I can see her waving her arm.
Good afternoon to all participants. So now it's 2 p.m. and this is our last day, or you can say it is a conclusive day for a week-long online FDP. Dr. Shankar Sehgal has also joined us. So any words from your side, sir? So can we start, sir?
Good afternoon to all. Sir, you please carry forward.
Okay, sir. So I formally welcome all the participants to this meeting. Today we have very renowned professor, Dr. Mohammed Gab from Egypt. So I will give a brief introduction about Professor Mohammed Gabriel. Sir, did you have joined? I think Professor Gabriel has joined us.
Yes, Professor. I'm here.
Yes. So with your permission, can I give you your short introduction to the participants, sir?
Sure, please.
Yeah. So Professor Gabriel is a metallurgist and having a background of metallurgy engineering. He got his PhD from Nagoya University, Japan in 2008. He worked in a Nagoya University. Then he shifted to Tohoku University, Japan till 2010. And then he moved to Egypt, Japan University of Science and Technology, Egypt. He is working as a professor of advanced material in Egypt, Japan University of Science and Technology. So since 2019 and leading an advanced functional metallic material lab. His research is focusing on alloy design and microstructure control of advanced alloys. He worked in developing a new generation titanium alloy for biomedical applications, ultra high strength titanium alloy, negative and zero thermal expansion alloys, and recently developed a new functional high entropy alloys. So basically his research is revolving around design and development of new generation titanium alloy. He received the state award from Egypt in 2014. Beside more than 15 national and international awards he has received, he was a visiting professor to many well-known institutes such as Tohoku University, Japan, and India. He usually visits to IIT Madras. He is also having collaboration in IIT Ropar. He also visited Michigan University, USA, Korea Basic Science Institute, Korea, and Joint Institute for the Nuclear Research, Russia. He supervised more than 20 MScs and 17 PhD theses. He shared in organizing 15 international conferences, and he was invited as a keynote speaker for more than 25 national and international conferences worldwide. He had 20 funded research projects, national and international, and he has published more than 200 reputed journal articles. In this publication, 10 patents are included. So in his name, 10 important patents are there. He has also published 10 book chapters, 100 journal papers, 90 international conferences, and having a citation more than 4,500. So, sir, I welcome you from the behalf of our organizing committee. I welcome you, and we are very grateful with your presence. And I appreciate that you have spared your time to join us in your schedule. Today is a Saturday. Still, you have you spared a time for us. Sir, may I kindly request you to begin your lecture, sir?
Yeah, thank you so much, Professor Sedho, and really I appreciate so much your kind invitation and the organizer, Professor Sigal, to give me this chance and opportunity to join you today. Actually, my lecture was planned to be yesterday, but I'm very happy to be in the last day. So
Yes,
to show you the conclusion of this intensive training course, it's my pleasure. So if
thank
you
you.
allow me, I will share my screen. By the way, the image is not appearing, is it? My photo is appearing?
Sir, your camera may be. Yes, yes, it is very clear. Your presentation is also there, and your image is also there.
Okay, great.
Please. Yes.
Shall I start now?
Yes, sir. Please, sir.
Yeah. So first I start with greeting all of you. Assalamu alaikum is in Arabic and konnichiwa in Japanese, or good afternoon as in Indian side. This training is about next generation biomaterials, which is my talk will be concentrated on the first part. Clinical translation through machine learning is explored by many of the presenters in this training course. Please allow me. Yeah, this is a summary of as Professor Sedo has introduced me. I joined the just after working in Japan and PhD in 2010, and I'm a professor of material science and engineering. Yeah, so it will be good that to share with you that our university, Egypt-Japan University, is a newborn university, is a research-oriented one. Actually, it is built between two governments. It's governmental agreements between two nations to build this university as a gate of, for Japan in Africa and Middle East. And it is research oriented. So we started in 2010, focusing on graduate studies only. Then in 2017, we started undergraduate studies, mainly in engineering, and later on we have introduced pharmacy and architecture and some other topics related to the technology. Our university is located in Alexandria. It is in the north of Egypt on the Mediterranean Sea, in a city called Burg Al Arab, New Burg Al Arab city. It is industrial city. It is around 2,000 in the factory. The objective was to serve this type of industrial zone and serve the whole nation and around. As Professor said, who introduced that I started was established my lab is advanced functional metallic materials, and we work in a wide scope, but the main scope is developing titanium alloys for biomedical applications, or not only titanium. We have explored more like high entropy biomedical alloys, as Dr. Noor has been presented in the second day of this training course. But we still cover other topics like laser processing of alloys, or aluminum battery, or shape memory alloys for stent application, and so on. And this is our lab facility. Our work started from the design of new alloy for different application, and basically biomedical application. And we produce the alloys after the design by electric arc melting furnace that can melt active alloys like titanium alloys or nickel alloys and so on in inert atmosphere. And we can process the ingots produced by melting by a rolling machine. We have a rolling mill. And then we can make heat treatments of the material, so we can control the microstructure and the properties, and then we can make characterization, mechanical, thermal, and metallurgical metallography, and other facilities is related to the same topic. So this is a story. We design alloy, we process, we control the microstructure, and we control the properties to fit with the application of object. So today I will talk to you about the progress in the design of new titanium alloys for biomedical applications. And since this training course is including some exam at the end, so I will be slow, so you can follow me in some topics. Actually, the objective of this training is to give you a full idea about this topic, and I will give you what's happening for a long time, and we are doing similar to what other people doing something, and sometimes we have some new ideas, but I present here only our story that in the progress, which is being done by many other research groups. Yeah, and in this work I present today, I have to acknowledge that I have many collaborators like Professor Sid, who I collaborate with him in many work. But in this presentation, I have to acknowledge Professor Morinaga at Nagoya University, Professor Ninomi at Tokyo University, Professor Hattori at Meiji University, Kobayashi at Ehime University, and Professor Allam at American University in Cairo, and Professor Muna Man'i in Dental School, Alexandria University, and many other students was involved in this work that I'm presenting today. So from the basic idea about material science and engineering, how it is the start point to develop new alloy to solve a problem of already existing alloy or material, we start from the composition. This is a general structure and flow of the material to be developed. So we start from the composition. We have to choose the proper composition to do the combination that's make cost effective and easy to produce and processable and so on. And then we have to process the material. We design or choose the composition. So we make the processing in a way to control the internal microstructure and to give the final shape of the product or the geometry and so on. And then maybe including from the processing is to make a heat treatment after the final product is shaped, whatever the shaping process, casting, welding, joining, rolling, extrusion, whatever the process is. So maybe also followed by heat treatment, so we can determine the final microstructure of the material. We engineer the structure by the composition and process. So we control the property by this link to the final microstructure we reach, which is variable and so on. So depending on this property, this engineering product or advanced product will perform in its final application part. So this is the story what we are doing we start from the composition up to performance and so on. Today we are talking about very special material that's used in a specific application, which is metallic biomaterials. Metallic biomaterials is widely used in many parts of the human body, like what we can use here, as you can see, some guide wire for the crowding of teeth treatments, or bone plates, or bone pins and screws, or spinal fixations, spinal rods, and so on, hip joint or knee joints, dental implants, and stents. So, and many others actually, but this is just examples of the metallic biomaterials is the main material used to solve these issues in the human body. So actually, this is metallic biomaterial is not only material engineering research work, but it is unique interdisciplinary research actually. And especially if we are talking about developing new material to solve what is existing and which has some drawbacks or some negative impact, especially after a long time of implantation, we have to consider some issues and we have to resolve by new material. So we are talking about new generation of metallic bioimplants and tools. So to introduce this new solution, we have to start from the material design itself, and then material processing, and then we can characterize the material, including the mechanical properties and corrosion testing and fatigue and many other things, many other testings. And then we go to bio related investigations, which is in vivo and in vitro testing, that we have to see how the environment, which is cells, human cells, different types of human cells, how it will interact to do the function of this implant that will work. So as you can see, it is multidisciplinary, interdisciplinary. So cooperation is a must to make this story as a success. And normally, if we're talking about a metallic biomaterial to be developed, it will take more than 15 years from the start of the idea to till we can give a technological solution, can go to the market and can be implanted in a human body. So there should be a cooperation between material engineering or material scientists and the chemist, biologist, surgeon, dentist. Many people should cooperate to reach to this success story. So in general, what is the problem that we try to make a new generation of metallic biomaterials? So the problem is some of the materials or metals has been introduced already in the market and already widespread in the market, was not originally designed to be for biomedical application. Yeah, it was designed for some engineering application, and the biological and biocompatibility issues was not started from the beginning, but these alloys already used in the market now was the most promising material. So we, after a long time of experience and using these commercial alloys, the researchers and people working in the field discovered some drawbacks and some problems. So they have to solve it. Especially as we can see, I can summarize here, there are some biological issues. So some of the alloys containing some elements that's toxic or allergic. Like, remember with me, nickel is allergic material, vanadium is a toxic material and the carcinogenic, cobalt is toxic material. So most of the alloys, as I will show you, containing these elements. And these elements has a problem. So we have to develop the new generation of metallic biomaterial. We should avoid these type of elements, which makes toxic or allergic reactions. And also, the material should pass the in vitro and in vivo assessment, as we will see today. So the material originally should contain no elements that make hazard or harmful to the human tissue, and can withstand for a long time without troubles. This is for the environment itself, but also the mechanical functionality. There are a mechanical functionality of this implant, metallic implant, to do the job. Some of the functionality is related to the property, which is high strength and fatigue strength, depending on the position and the shape of the material. That will shape a product, a piece of implant. One issue was discovered, actually, it was not considered from the beginning to choose the commercial alloys, which is the Young's modulus. They discovered that the elastic modulus of most of the alloys used already in making implants has high mismatch with that of the bone. So they have high Young's modulus, and they have to solve this issue. Actually, it is a serious one, and this was one of the main reasons of the failure of the implantation, because such type of mismatch in the elastic modulus between the implant itself and the surrounding bone tissues. And also the ultimate wear resistant, it should have high wear resistant in order not to release some debris during operation after implantation, I mean. So these debris will release ions or something like this. So if the wear resistance is not good, there will be some release of debris, and these debris will release some ions. And we have to consider the other chemical stability of the material after implantation, because the human body is a severe condition actually for any material to be located in, other than mechanical and biological, but also the body fluid itself is a corrosive media. So the material should have a high corrosion rate, a low corrosion rate, high corrosion resistance. Many of the failure of the implants is related to the corrosion. So the material corroded, and the dimension is changing because of the formation of the oxide layers, and there are loosening of the implants after this one because of this type of corrosion. So we have to consider this one very carefully. Also, high resistance oxide layer. It is important actually to have this oxide layer formed on the surface of the alloy of the implant itself to be compact, so it can prevent the corrosion to continue in the material and make the failure. And to all, the very low ion release is very important, because if high ion release due to the corrosion or due to the less compact layer of the oxide layer on the implant itself, so many ions will release from the implant itself, go to the human body, and will interact, and then will reflect on the biological response itself, how the cell will treat with these ions released to the body, and is it overdose or less than the or in the acceptable range of the dose, and so on. So I can show here how this debris or ion release is very critical, very, very critical, that will determine how the body will accept or reject, or will be safely heal the problem in the bone or whatever. As you can see here, if this is the biomaterial or the implant has been implanted, yeah, the implant itself, there should be some very micro scale scratches or something like this. Even during the operation itself, during the implantation operation, the surgeon during in the operation room, there will be some debris release after implantation, and this is actually the surrounding tissue. This is surrounding tissue. This is the interdistance between the implant and the bone itself, if it is inserted inside the bone. So this is a bone, and how the bone itself will react with the implant after implantation in the operation itself, from time scale and length scale. After only 1 second from the implantation, the protein will attach to the implant surface, and will interact with the particles, debris. During the operation, there will some debris is released, and some ion will be released, which is only travel distances 10 nanometers, very, very short time in very short length scale. So after 1 day, so this debris or ion will release, will travel inside the human tissue, and we can see here that there are some cell response will interact with all these type of debris and ions released from the implantation, and then the bone itself will react. Will it heal up, and will build new cells in order to to recover this type of fracture or so and so on or not. So as you can see here, yani with a few days or a few months, there should be a decision that the body will accept this type of implantation, or the healing will be progressively or will be hindered or will interact positively or negatively to the implant itself. So it is very critical to know the material itself from the component of the material and how the body will interact with it. So this table summarized the different element itself, how it will interact differently with the human body from biocompatibility point of view. So this is a biocompatibility which about the cell, how it will interact. The color here representing yes or no. Yes, that means good and is acceptable. That or if it is red, it means it is not acceptable and it will make trouble. So here is summarized the whole elements that's composing the different alloys, and this work is cooperated in cooperation with Professor Sido. Actually, we have revised this table, and the element itself about it is carcinogenic or not, it is genotoxic or not, it is mutagenic or not, cytotoxic or not, allergic or not, corrosivity, and so on. And a cost was another factor we have considered, as I will explain to you today. So if it is green, this means this element is good. It's acceptable to be used for making implant. If it is red, it means it is not good one. So as you can see, the elements which has many green is like titanium and zirconium, niobium, molybdenum, tin, something like this. And you can see some elements that is in the range of midway. That's something is good, something is not acceptable, like manganese, iron, aluminum, and so on. And some elements are very bad, almost red in all type of reaction with the human body, is like nickel, cobalt, chrome, vanadium. All these are very toxic materials and carcinogenic, and many makes many troubles. So if this is the case, so we have to think about the commercial alloys already used in this field. Does it contain these elements or not? And if yes, if it contains, so we have to make a new alloy that's mainly composed of these alloys, of these elements, okay? And the cost will be another factor, as I will explain to you. So unfortunately, the common biomedical alloys, the most common biomedical alloys are these alloys: titanium, 6 aluminum, 4 vanadium. Titanium is good one, perfect, okay? But 6 aluminum, and aluminum is here, has some issues. And vanadium is here. Very, very, very dangerous. So vanadium is a big problem, actually. However, most of the implants... Sorry, are you hearing me? Hello?
Yes, sir. Yes, sir.
Okay, shall I continue?
Yes, sir.
Second floor. Sorry.
Alish, Dr. Alish Kumar, please mute your mic.
Yes.
Sir, please
Okay,
continue.
so yeah. So we can see that this most common alloy is has a trouble, actually, from compositional point of view. And the second one, second most used one, is cobalt, chrome, molybdenum. Cobalt and chrome and molybdenum. Molybdenum is okay, but cobalt and chrome are from here category, from this category. So it's a problem. And 316 low interstitial stainless steel is very common, actually, to make implant. But stainless steel made of mainly iron and nickel and chrome. Nickel is here and the chrome is here. Okay, so also stainless steel has an issues for long time implantation. That's why most of the implants, as you can ask any surgeon, he say the implant maximum life is 15 years, from 10 to 15 years. After that, you have to revise it. You have to make revision surgery. You have to open again and take it out and insert again. So this is a big issue. For example, if we make an alloy made of the compatible elements, which is like titanium, niobium, tantalum, zirconium, and so on, compared to the stainless steel, you can see here, this is a real in vivo test after 52 weeks of implantation of one of the alloys that's composed of the biocompatible elements and compared to that of stainless steel. This is a bone plate to heal a fracture. There were a fracture here in the tibia. So we can see the alloy that's composed of the biocompatible elements. We can see here the bone is grown again. It is compatible with the plate itself. So there are a growth of the new bone cells has been grown on the and there are big or much better adhesion of the plate with the bone itself if we compare it to the stainless steel and so on. So this means the bone itself will respond to the implant itself differently depending on the composition of the alloy. Okay, so the other issue, this is from biocompatible point of view. From the mechanical biocompatibility, we need high strength in order to, especially for the application which is load bearing, like hip joint, knee joints, and dental implant. So some of the parts are load bearing, so it should have high strength in order to do the mechanical function after implantation. And high fatigue resistance many times is very important, especially in the moving parts, like, as I said again, hip implant or knee implant and many other things, because it will be exposed to cyclic loading. So for long time implantation, it should have a high fatigue resistance of the material. And what is a big issue, actually both those two characteristics are already met in the all commercial alloys. But one more mechanical characteristics is not meeting actually in most of the commercial one, as I will show you, is the low elastic modulus, especially for the hard tissue substituting instruments. Actually, we need to have low elastic modulus alloy in order to have good matching with the bone itself. Another mechanical functionality is needed, like super elasticity, and in some application they need very high stiffness, other than the low Young's modulus, completely opposite. So this is for very special parts of implants, like spinal rod, like guide wire of the dental fixation, and so on. Okay, so the issue of Young's modulus, I'm explaining here why it is a big issue and we have to treat it. As you can see, if this is the human skeleton, human bone skeleton, and if we are making a hip implant here to transfer the load from the upper part of the body to the lower part of the body to the head itself. So the load will transfer from this way to this way through the implant itself. Okay, so let's see the commercial alloy itself. How is the Young's modulus? The cobalt to chrome is more than 200, stainless steel same, and some of the titanium alloys 110, 20 or something like this. Okay, if we compare it to the bone is very small, is less than 20 gigapascal. As we can see here, is very big mismatch in the elasticity. So the load when it will transfer here, and if this one doesn't bend enough to match the bending of this surrounding bone in the hip itself, there will be a very big mismatch in the bending behavior itself. So this bone will not will bend, but this one will not bend. So the load itself will not transfer here, will transfer only in the small contact, because this one is stiff compared to the bone itself. So the load itself will transfer only in very small contact zone in the tail of the implant itself, and this part of the bone itself will not carry load. And subhanallah, yani God created us that the bone itself can sense the load and accordingly take action. If it senses the load, there are a cell called osteoblast. This osteoblast cell is ordering the cells to be created, to be new cells to be generated. If no load, no request, no sensing, no load sensing, so no new bone cells is generated. So because this part is doesn't feel with the load itself, because the whole load comes here. So this means the stress is shielded in this area. So this bone becomes weaker and weaker and weaker, and later on it becomes less dense. Later on it becomes loose with the implant itself. So the operation is failing. So the implant itself will not continue with success, because of there will be some loosening between the implant and the bone. And this criteria called stress shielding phenomena, and we have to avoid it in this sense. So we have to solve this problem, because this is the already commercial used alloys for making implant and so on. We have to solve this big issue actually. So if we consider the most common alloys that close to that of the bone from Young's modulus point of view is titanium 6 aluminum 4 vanadium. And this alloy has excellent plastic properties, yield strength, ultimate fatigue, and many things. But again, if we check the composition, they have a vanadium, which is toxic, carcinogenic, and many issues is concerned with vanadium and aluminum. And the other one is the elastic modulus mismatch. The elastic modulus of this alloy is quite high compared to that of the bone. So there are stress shielding phenomena in this alloy will appear. If we compare to nickel titanium alloy, it's composed of big part of nickel. Nickel is around 50%, and nickel has allergic effect. And 20% of males has nickel allergy. 10% of females worldwide has nickel allergy. I'm one of the nickel allergists. So if you make this one, which has excellent elastic property, the elasticity is good, much better than here, but it contains big amount of nickel. So we have to consider that the mechanical mismatch is okay, but the compositional and the biocompatibility is a big issue we have to consider. So the scientists and the researcher give a focus on the reduction of the elastic modulus of new generation titanium alloys, or alloys to become to work in the biomedical field. And from the beginning, we have to avoid the toxic alloying elements from the element itself, from the alloy itself, so we can have from the beginning give a good solution for the biomedical alloys for the new generation. So there are big stories in this one, and I summarize that to say that beta type titanium alloys are excellent candidate for this application. That we can have a beta type from non-toxic elements alloys, and in the same way we can have low elastic modulus beta type titanium alloys. So beta type titanium alloys is a good candidate for the next generation alloys for biomedical field. Okay, and I know that in this training there were one lecture about the basics of titanium and the classification and so on. So based on what already should be explained, I will summarize here that titanium alloys are different types of alloys. Some, if we alloy titanium, this is the phase transformation. And if we add alloying elements here, if the elements is stabilizing alpha phase at room temperature, the room temperature phase, if it stabilizes alpha phase, that widen the zone of the alpha appearing zone, called alpha stabilizer. If it is doesn't affect the beta transits from alpha to beta transformation point, we call it neutral. If it is stabilizing the beta phase, take beta phase to a lower temperature, so widen the zone of beta appearing zone, so we call beta stabilizer. There are some types, two types of beta stabilizers, is isomorphous one and eutectoid one. So both elements are beta stabilizer. From the beta stabilizer, they are like molybdenum, vanadium, tantalum, niobium, iron, manganese, chrome, nickel. So all these one are beta stabilizers. Many of the elements are beta stabilizers. Alpha stabilizer is very small: aluminum, oxygen, nitrogen, and carbon. Neutral elements like tin and zirconium and so on. Okay, if we see this figure, and it is a very important figure actually, that see how the beta stabilizing elements, if we add it to pure titanium, this is pure titanium here, and this is the temperature of the phase transformation from alpha zone to beta zone. If we increase the alpha, the beta stabilizers, we can take the beta phase to lower temperature, as you can see here. Actually, beta titanium alloys is of martensite forming alloys. That's, we have a martensite phase. The martensite phase is a phase happens without diffusion. It is diffusionless transformation. So we call the temperature at which the martensite phase starts to appear by cooling. Martensite start MS. MS temperature is going this way, and MF, which is the martensite finish. By cooling the alloy, this is a specific alloy. It is beta phase. When it comes here, the martensite starts, martensite finish. So we have fully martensite. So this phase is the martensite alpha prime phase, alpha double prime phase, and so on. Anyway, if we MS, the martensite start transformation comes to room temperature. So at room temperature, this alloy, we have a beta phase, but we call it metastable beta phase. So this is a critical composition of beta phase, where beta phase becomes at room temperature predominantly and in metastable phase, in metastable state, not stable state. So it is very critical, actually, this composition, that we take the beta phase at room temperature metastable, because this zone is unstable. We can, even by deformation, the transformation from beta phase to martensite can happen, even it is the MS martensite start is below room temperature and so on. So this is a very critical beta phase composition. Yes, so researchers did a lot of work to develop beta titanium alloys and avoid aluminum and vanadium. So aluminum and vanadium free, or developing beta type titanium alloys in the research done up to 2020. As you can see in the Scopus, that's big increase, monotonous increase in the developing new alloys that is beta type and doesn't contain aluminum or vanadium, which is toxic elements and so on. So many work has been done to develop many alloys, beta type titanium alloys, that doesn't contain aluminum or vanadium, and to be biocompatible, and also to work in show biological biocompatibility, and show high strength and fatigue resistance, and in the same time that show low Young smoothness. As I said, all these characteristics are needed for the next generation medical implant alloys. So this table is summarizing what was the first generation of alloys that used in implant manufacturing from 1950 to 1990. they use commercial pure titanium or titanium 6 aluminum for vanadium or some modification in this one. All this alloy was commercially used, okay? And as you can see here, it has a Young's modulus of above 100, 110 and something like this. And it is, yeah, the tensile property is good, no problem. And it is from the alpha plus beta type titanium alloys. But actually, the researchers from 19, they started to develop the beta type titanium alloys and metastable beta type alloys, which they can add many alloy, the big portion of the beta stabilizing elements like niobium and tantalum and molybdenum and so on, so they can stabilize the beta phase. And in the same time, these elements are biocompatible, doesn't have a problem with the human body. And in the same time, the Young's modulus is lower, much lower than this one. And this one is what we call it the second generation biomaterial. From 19, they started to produce this one. But unfortunately, many of it was not successful, as I will explain later. But as you can see here, it is from those type of beta type titanium alloys. So if we are further improving how to design beta type titanium alloys, we have developed a diagram called BOMD diagram. So this diagram is based on molecular orbital approach to calculate basics, the bond strength and balance and consider atomic size and every electronic parameters of the atoms, different atoms, to alloy titanium with different elements, and we can see in this diagram we can construct this type of phase zone that any alloy is located around here will be beta type alloy. If any alloy located in this one, after calculating from the composition point of view, will be alpha type. If located in this zone, will be of alpha plus beta type. How to do it? This one. So we say this is pure titanium, and if we alloy it with, for example, to make this alloy, that's titanium, 10 vanadium, 10 tantalum, 5 molybdenum. How we locate it in this BOMD diagram? So this diagram is used to the design titanium alloys, so we can predict the phases and so on as follow. Okay, so we go parallel to each element. This is the vector of molybdenum. This is a vector of tungsten. This is a vector of niobium. This is a vector of tantalum. This is a vector of chrome and so on. So we go parallel to vanadium. We have 10 vanadium. We go to parallel to vanadium with 10%, which is located as the arrow zone. And then we go parallel to tantalum. This is tantalum with the distance, the vector as here. And then parallel to molybdenum, and this is molybdenum vector. So the alloy will be located here, as you can see. This is the final location of the alloy. So this alloy is located in the beta type alloys. So this composition from the beginning, we know that it is beta type alloy because it is located in this position in the beta type zone of the BOMD diagram. So we can design, we can predict the phases very well from the beginning. We can predict the microstructure and so on. Okay, so we constructed this big map, and some very important alloy was developed by Toyota Research Center called the gunmetal in 2003, and they published in Science journal this development of gunmetal, which is located in this map here. And as you can see in this map here, we can see that it is in the critical zone of the zone where beta phase appearing and where the Martensite there, and this is alpha plus beta and alpha and so on. So this map by this way, we could construct for different alloying elements or different alloys developed. We plot it in the map, and we can see that all alloys located close to this boundary, the boundary between the single beta phase boundary and the martensite boundary, we can see that Young's modulus is decreasing if we go up parallel to this boundary line. And as we can see here, that Young's modulus is the values in brackets, as you can see here. This is the Young's modulus of any alloy located here is from 70 to 80. The Young's modulus of any alloy located in this boundary is from 60 to 70. This is empirically. This is already experimentally confirmed. 60, 50 to 60, and we can have also here 45 gigapascal. So this means that using the POMD diagram is very useful to predict the phase stability itself, and the phases will happen, and also Young's modulus. So according to this diagram, we can have low Young's modulus here, and we can choose the alloying elements as we like. As you can see, it is very easy methodology to use this type of vector. So we can choose it to be located here in with the elements that's biocompatible and so on. So it was very interesting piece of work actually, and this paper is published, is cited more than 1,000 times actually to use for developing and understanding the mechanism of how to develop alloys. Okay, so if we take, this is for an alloy, multi elements, but if we are talking about single element, yani titanium is alloyed with only one element, like for example niobium, and empirically this is experimental values, how with increasing the niobium content, what is the phases will present in the alloy. We can see at small amount of niobium we have alpha prime martensite, and we have alpha double prime plus alpha prime, we have alpha double prime. So there are variation of the phases formed along the curve by increasing the niobium content. And if we, and from this point, this is a beta C, beta critical that I showed you before. So at this amount of niobium is enough to stabilize beta phase, and more than this amount of niobium, all are beta type, metastable beta type. We can see, depending on the phases, depending on the phase variation, and this actually is exact or typical example for all binary titanium beta stabilizing elements. We can see all similar, this one, but different values of alloying elements. Okay, from this diagram, we can see that the smallest or lowest Young's modulus is located around this peak. So at the boundary between the beta phase and the beta plus any other phase, we can get the lowest Young's modulus, as exactly we have said in the BOMD diagram. So using this meaning and understanding, we developed some alloys that's containing the zirconium, which is biocompatible, niobium biocompatible, tantalum biocompatible. So simply we use these biocompatible elements to stabilize beta phase, and we further add very small amounts of oxygen and iron because they are strong, effective on the phase stability and so on. So very small amounts are used to make big variation in the stability, so we can achieve the targeted stability level of stability of the beta phase, so we can get the needed microstructure and the mechanical property and Young's modulus and so on. And these different alloys we developed, we tested in the cold rolled condition and solution treated condition, different processing. And let's see, this is solution treated, this is cold rolled. Okay, we can see the ultimate tensile strength is increasing by increasing the stability, which means adding iron and oxygen will stabilize the beta phase more, and so on. So we can see here that the strength is increasing with just a small addition of oxygen and iron. And Young's modulus, actually, we could achieve very, very small Young's modulus. It's around 40 gigapascal for this alloy. And by increasing the strength, the Young's modulus is still also increasing, but not very high. So it's still below Young's modulus, below 60, which is close to that of the bone. This is the bone range and so on. So this is very interesting and very promising alloy that we have developed with low Young's modulus, high strength, and so on. And we have tested this alloys with the in body simulated fluid for the corrosion resistance, and it showed very high corrosion resistance. So this is our alloy. If we compare it to titanium 6 aluminum 4 vanadium, you see the corrosion rate, or this is high corrosion, which is representing the corrosion rate. We can see here that it's almost 10 order less than titanium 6-4 vanadium, 6 aluminum 4 vanadium. So this means very high corrosion resistance than the commercial alloy itself. And so mechanically is compatible. Corrosion resistance is much better. Young's modulus much low, as explained. And also we do tests for the biocompatibility itself. So we make in vitro tests for LIHA cells to see the cell viability cultured over this type of alloys for 2 days, and we can see that the cells is almost have the same viability, very good viability, which is close to 100, and the acceptable is above 80. So all our new alloy is very promising from the biocompatibility point of view, from the corrosion resistance point of view, from mechanical property point of view, and so on. So this was very interesting and promising alloy for the next generation alloys. Actually, this type of alloy we propose to use it for manufacturing of stent, self-expandable stent. Actually, in this work, I cooperated with some people, Professor Allam in American University in Cairo. So I'm material and he was a chemist, and we use a pharmacist. The student was a pharmacist, and we use also the textile people to design the stent geometry itself, and so on. We did the proposal and we filed the patent that actually after this stent itself, we can grow on the surface of this type of stent oxide nanotube by anodization process, and this work is published in scientific reports. So these oxide nanotubes grown from the metal itself can be filled with drugs, and these drugs we can control the amount of the drug by controlling the nanotube size and the length of the nanotube. This is a nanotube size on the surface of the substrate of the alloy, our alloy. So we can have different geometry of nanotubes, and so we can have different loading of drugs, so we can control the drug release itself. And we filed this as a US patent, and it was granted in May 2020. It is very, very interesting work, actually. Not only this, actually, I mentioned in the beginning that there are something called superelasticity. Superelasticity, many of you are mechanical engineering background, so we have the stress strain curve of the material that we load the material, and it has a strain. This is the stress, and this is the strain. Strain is only related to how to say to the stretching in the bond between the atoms itself till we reach the yield point, something like this one. So we start to plastic. So plastic means the bond between the atoms is broken. But in superelastic alloys, it is not the case. Actually, the atoms are rearranged itself and can accommodate some strain. And by removing the load itself, the atoms return back to its position. So this is not really plastic, but it is, we call it pseudo-elastic. That's not true plasticity, but it is a type of elasticity, so we call it super elastic. Normal material that has elasticity is around 1% plus or minus something, but here we developed a new alloy that is very super elastic, and we can train this alloy by loading and deloading. We load and deload at different loads, and to train the material to accommodate higher pseudo elasticity, high super elasticity. You can see here, this is the cycling loads, first cycle, fifth cycle, 10th cycle. So the shape of the stress strain curve is changing, as you can see here. And the total amount of strain is recovered when we train it at 300 megapascal, we can recover 3.5% strain by compression. And if we train it at 500 megapascal, we can recover 5.4% strain. This is very big, as you can see. By loading and deloading, we can recover 4.5 fully recovered strain. And by changing the composition, okay, so this is actually a different way of training, and we change the different alloys and different phases stability, so we can tailor the super elasticity. So this is material that doesn't show super elasticity. It goes up and down, loading, deloading. Another alloy is this one. This is a maximum elastic strain can accommodate, is around here. This is 2% scale bar. And as you can see, this alloy can accommodate elastic strain that by loading and deloading up to 9.5, which is quite high. It is a huge amount of elastic strain we can accommodate in this alloy. Actually, it is a very promising alloy we have developed, and very promising. And also, it's a new type of training process that can be used for making spinal rods, or making the wire guide for the dental fixation, or making that type of self-expandable type of stent, or making the tools for dentistry or many type of surgical operations. And actually, we have filed the patent for this alloy and the mechanism. Yes. Another work we did is to develop similar type of alloys, but for different type of stent. Yani stent has a self-expandable stent that needs super elasticity, and another one doesn't need super elasticity, but should accommodate big plastic strain. We should have big plastic strain of the material to make a balloon expandable stent. Balloon expandable stent is inserted by an endoscope to the artery or band that has narrowed, as you can see here, and we make inflation of the balloon, so it expands the stent to open the artery or the band, and then deflate the balloon, so we can take it out. So we leave the stent there opening the vein or artery, and so on. So this type of mechanical functionality is two things actually. One, we need some mechanical property during the opening of the stent, and we need another mechanical, which sometimes different or sometimes contradict the opening parameters, but to withstand the forces and the blood flow and so on. So we have to design the material to have a very complicated way of mechanical property related to yield point, the work hardening rate, ultimate tensile, and the homogeneous engineering strain, and many parameters should be treated actually. And we developed some alloy, and we filed the patent about this one. And important thing actually is extra function is needed for making such type of stents is after implantation, we need to make diagnosis of the status. And we have to test like using CT or MRI testing, so we should know the position and the status of the stent after implantation. So the magnetic resonance is very important and the characteristic very important, and we have to consider of the alloy itself, and we consider this one from the design point of view, and our alloy showed very promising magnetic susceptibility compared to the commercial material that used for stent application. Okay, if you don't mind, I can stop here to receive comments before I proceed for the second part of my presentation.
A very informative presentation given by you, a practical information, because this information is very important. So, participant, if you have any question, you can ask Professor Capri. You can unmute your mic and ask the question.
Good afternoon, sir.
Okay.
Sir, we are basically working on this coating in the alloys for making it corrosion resistance.
Yes.
So is there any scope for we can try this new alloys with coating, sir?
Coating?
PO coating, plasma electric oxidation.
Yeah,
Actually,
please.
yeah.
The sound is not clear for me. Could you please repeat again,
Yes.
or Professor Setu can explain?
Sir, it is plasma electric oxidation, PO coating, PO.
Oh,
Micro
okay.
arc oxidation.
Yeah. Actually, this is a new trend to use it for the to improve the biocompatibility of the material and the functionality after implantation. But it is sure applicable for your investigation.
Okay, sir. Is it
interesting actually is our alloys that we are producing as very inert, as I showed you here, that the corrosion resistance is very small because it contains some amount of zirconium and niobium, and zirconium and niobium give very dense oxide layer itself, so it is very safe, very inert.
okay, sir? Okay, nice session,
If we
sir.
compare it to
Informative.
titanium 64, it is almost 10 times higher resistance in corrosion.
Okay, sir.
So naturally, the coating, if you are doing a coating with a biocompatible material, it will enhance the also integration, and also it will
Yes.
give a good corrosion resistance.
Yeah, to add another function.
Yes. So any other question from the participant, please?
Good afternoon, sir.
Yeah, good afternoon.
Yes.
Sir, I wanted to know that you have shown various alloys and for the this as a biomaterial. So what will be the consideration for the ratio? For example, if I can see in the slide, this is titanium, aluminum, and vanadium. So what is the probable ratio? Based on what we are considering the ratio for the preparation of that particular alloy?
Yeah, thank you for your question. Actually, this is a story. My whole work during the last 20 years almost is how much amount of the material that we use and to achieve what. So the story is how much amount of elements to achieve which phases, and the phase sure will determine the property we are talking about. If a phase is soft and we need application hard, so this composition is not good enough to do the function. So we have to change the composition in order to achieve a phase or combination of phases that make it hard. If an application is needed soft, so I have to choose the phase, the composition that make the soft phases, and so on. If an application needs pseudoelastic, which is super elasticity, so I have to have metastable type of beta phase that by force it can transform to martensite, can accommodate some strain. So this is a key story of our work. Actually, we control the phase stability by the composition in order to achieve the required mechanical property. Shall I? Could I answer your question or not?
Yes, sir. Yes, sir. Okay, sir. Sir, one more thing is, like in alloys, we are having more than two material or two material also, and the individual material have separate toxicity or separate maximum tolerated dose to the organs. So how, like this is based on your strength and based on your requirement. But now my question is, like their different metals have different toxicity. So apart from that mechanical strength, we should consider the toxicity also. Then in that case, what we should consider, like we want to maintain the stability as well as young modulus mechanical strength, but parallelly we have to see the toxicity also. Then in that case, what we should consider?
Yeah, actually what we do and what everybody is trying to do from now is, from the beginning, we avoid that elements that make troubles and already known to make troubles, toxicity and carcinogenity and so and other things, and allergy or something like this. So we have to consider these elements to be avoided or to be minimum. Sometimes it is very important to add mechanical functionality or chemical functionality, but it has adverse effect on the biological response. So we have to make it in the minimum amount that will make minimum effect in order to meet. As you can see, it's a combination of many properties should be met together to do the function for a specific product. So this is, we have to be clear from the beginning that the elements that makes troubles to be avoided or minimum from the beginning. And if not, we have to find alternative element.
Okay, sir. Thank you, sir.
Yeah. You're welcome.
Any other question, please? Okay. I think we will move to the next slide.
Shall I move to the next part?
Yes, yes.
Okay. So what I have presented is very interesting, actually, but we still have a problem, actually. And we developed many good alloys, and many research groups have developed different alloys. It's very promising in some way, but they face a very big problem, actually, is to convince the companies for commercialization. As I showed you before, that's the first generation containing toxic and allergic elements. And the second generation, which is much better, but contain big amount of niobium, molybdenum, tantalum, and so on. And these elements are not common elements, actually, and it is expensive elements, and it is high melting point elements. Although they are very good in the mechanical and biological point of view, but company to replace cheap, very common, very well used, very easy, well established technology to produce it with a cheap, more expensive, difficult to produce, and elements not common that will be controlled by some countries is a big issue for the companies to produce new implants, which is much better for the patient, but company doesn't accept easily, especially in the poor countries or the countries with low economics. So it's a big issue to find this type of good and much better alloys to be used for commercialization. So we have to consider again is to reduce or avoid these rare elements because of the cost consideration, and also to avoid the high melting temperature elements because of the production technology difficulty. So tantalum, the melting point of niobium and tantalum above 2,500. It is not easy to produce, and molybdenum and so on. So is a big difficulty, and the cost is another issue, as you can see here. Titanium, the price of titanium per kilogram is around 11 US dollars. Okay, vanadium is very expensive. Tantalum is very expensive. Niobium is expensive, and they are not abundant in the Earth's crust. And if we consider alternative elements like tin, manganese, some amount of iron, and so on, which is much cheaper elements and more common. Every country has it. So it's another issue. And this big issue was raised from the beginning of 2005, after many work has been done. So we have to consider this one in order to achieve same functionality, mechanical functionality and biomedical functionality with a better cost, lower cost, and keep low Young's modulus and so on. In this one, I started work, which was in the early time of this issue, that to produce low-cost biomedical implants, biomedical alloys. So I developed an alloy composed of iron is the major elements. Iron is dispute elements, which is in between. And I used small amounts of the biocompatible elements, so technologically easy to produce. Cost consideration is much lower than all alloys that we have produced in the first part of this presentation. So we use again the BOMD diagram in order to be a shortcut, easy to reach the composition of interest. As I said, if we want to have low Young's modulus, we should go to this boundary between beta phase, single beta phase, and the beta plus other phases. Just crossing the boundary, we will have the lowest Young's modulus. So if we are talking about this system, I expect that depending on the amount of iron, 2% iron, this is pure titanium, with fixed 3 niobium, 3 zirconium, 2, 3, 4, 5, 6, and so on. Depending on this one, so number 4 and 5 will be just the boundary, crossing the boundary of low Young's modulus alloy. So using the same technique, BOMD diagram, to design, to predict the phase. Yes, we can see here the phases of the alloy. For 2 iron, 3, 4 iron, 5 iron. Okay, so this is beta plus martensite, 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 and at 5 is the first single beta appears. So yeah, as predicted, actually we predicted from the BOMD diagram that this alloy will show the single beta phase with low stability. And if we measure the Young's modulus by resonance and by tensile test at different condition, hot rolled condition or solution treated conditions, okay, it showed lowest Young's modulus we can achieve around 80 to 7 to 8. So actually, this alloy is lower cost, much lower cost than the previous one that we could achieve. Yes, Young's modulus little bit higher, little bit, but much lower than other commercial alloys, and the cost is low. From technological production point of view, it is easier because we use iron, small amount of niobium, and so on. And this one was very promising alloy from the cost consideration. And mechanical property point of view, you see the mechanical is very high, even much better than the previous alloy we have developed and many people has developed. So the ultimate tensile is around 1000 megapascal, which is quite high. So this was a very promising alloy. So we go for the in vivo and in vitro test. So this is an in vivo test, and after making the implant rods of this alloy and was implanted in rabbit tibia and for some different times, and we can see the implant, how the bone is grown around the implant here. If this is our alloy, 5 iron, 3 zirconium, 3 niobium. And compared to the 6,4, we compare to the reference alloys and compare to stainless steel 316L. And this is an implant and this is a grown bone. We can see here that the bone grown around the implants very nicely. 6,4 is also grown, but the stainless steel, the bone doesn't grow well after 6 months implantation. Another important issue is the adhesion between the implant and the bone itself. We can measure how the adhesion in the contact area, because you know this one is normally is homogeneous depending on the cut position, but the adhesion is very important and very critical. So the radiolucent line of the implants of our alloy is very small, so this means very high adhesion. So the bone like the implant and grow and attach to it very well compared to the 6,4 and the stainless steel. It's much better than this one. So this means that our alloy is very promising. And not only this cost to consideration we have done, but we did another play actually. So do you remember I showed you before about the Young's modulus is change with the beta stabilizing elements content. Most of the beta stabilizing elements show this type of change of Young's modulus depending on the phases and so on. In the last work we did, we could catch the single beta stable phase here, which is the first peak. Okay, so the single beta phase peak. But another way is to catch the other peak, which is single martensite peak. Okay, so the Young's modulus is a little bit higher, but the amount of elements is much lower. So if we add much lower amount of elements to the alloy, this means lower cost, much lower cost, and we keep titanium as the majority of the elements in the alloy itself. Okay, so we try in the same way. We developed some different alloys based on molybdenum, small amount of molybdenum, and amount of iron to stabilize the beta phase. So again, using the BMD diagram, we developed the decompositions. So at the single beta phase, this alloy is here, is located here, okay? And the other peak, so this is the peak of single beta phase, and this is a peak of martensite, here, located around here, of martensite phase, okay? So let's see, compare these two alloys, is the first peak of single beta phase and the smaller amount of elements, which is, as you can see here, only 2% and 0.5% iron, very small. From a weight point of view, actually, it is very important. As you can see, this is if we compare to titanium 6,4 alloy, our new alloys compared to stainless steel and the commercial TNTZ alloy and the cobalt chrome molybdenum, cobalt chrome tungsten alloy. If we consider the cost point of view, our alloy is half the cost of titanium 6,4. Okay, from a compositional point of view, and almost like stainless steel. Okay, and very small compared to the recently developed second generation alloys, which is like TNTZ and cobalt chrome tungsten and so on. From weight point of view, actually, because if we are making a hip joint, the hip joint is almost 2 kilograms or something like this. If we made it from our alloys, if we made it from stainless steel, it is almost half. If we made it from cobalt chrome, it's much different. So it is easier, much better for to make hip joint from our alloys, from weight point of view and from cost point of view. Okay, let's go and see the properties of these alloys. This is that alloy that had the beta single beta phase. It showed Young's modulus around 83, and tensile strength is high, quite high compared to titanium 64. And the other two alloy that's hit martensite is almost same value, and both of them is lower than titanium 64, and the elongation is in this range, as you can see, and the strength is in this range actually, which is very close to that of titanium 64 or comparable to titanium 64. So again, our alloy is better from Young's modulus point of view, better from cost point of view, and better from biocompatibility point of view. And here our three alloys. This is alpha. This is the martensite one, and this is the single beta phase compared to titanium 64. You can see after implantation for 6 hours after incubation of the cells. This is the bone cells, what you call it, osteoblast cells. After incubation, we can see the cells, how the cells grow, and the shape of the cell itself, the shape index. We can see in our alloy here, the cells is growing and the number is big, and the cell itself is healthy, is big. If we compare it to titanium 64, the cell itself is dying. As you can see, it becomes thinner, not healthy cells. So from number point of view and from health point of view, our alloys are much better than titanium 64. And from cell viability, as you can see here, is compared to titanium 64, our alloys is much better and so on. And very recently, actually, we make in vivo test for these alloys, and it was very promising compared to titanium 64. One more thing, actually, I don't know how much time I have. How much time I have?
So 5 minutes. 5 minutes more, sir.
Okay. So another one is we work on titanium 14 manganese alloy that's lower cost if we are comparing to other titanium 64 or other titanium alloys or even stainless steel. The cost per kilogram of this one is very small compared to other titanium alloys, and we make many modification, and it showed a very promising strength, so it can work for some application in the biomedical, not any, because we have 14 manganese, where the biocompatibility was confirmed and it was acceptable. We make modification by zirconium addition to achieve different mechanical properties and different ductility and malleability, and it was very, very successful actually. This titanium 14 manganese as a low cost, very promising low cost alloy system that show very high strength and very good corrosion resistance and ductility and malleability. And this is a corrosion is much better than commercial pure and titanium and annealed alloys. Titanium 64 annealed 4. So our new alloy, titanium 14 manganese zirconium alloys, showed very promising actually. And also we make sometimes some surface modification, and we filed a patent in this one actually by making bioglass coating on the titanium surface to make it super hydrophilic bioactive coat, so it have very good matching with the implant itself, especially in the dental implant is very important. And recently we make some work, as Dr. Noor presented to you, we used AI in designing the new alloys that save some more time in using neural networks. So and we have very good achievement in this work actually in collaboration with Seth. So I go to conclude that many excellent titanium alloys recently developed and showed competing compatibility compared to commercial ones for different biomedical applications, including high strength Young's modulus, high corrosion resistance, easy processing, low cost, good biocompatibility. However, further in vitro and in vivo tests are needed followed by clinical trial for official approval and the potential commercialization. And in the coming step, it's a must to have a collaboration with those who are expert in the coming step. And I wish that all this story will lead at the end to a commercial biomedical alloy that solve the current problems and challenges for the commercial alloys in the biomedical field. Thank you so much all, and thank you so much, Professor Sedhu, for this chance. I am ready for answering any question if there are.
Participants, do you have any question? Please ask.
Sir, am I audible?
Yes, please, Vipin.
Sir, how this alloy is manufactured through casting, right? Sir, casting.
Casting, we produce normal casting by arc melting, or it can be introduced by induction melting, skull melting. Any type of casting is processable, no problem.
Also, before going for this in vivo test, do we do any surface modification, sir? In vivo test.
Some application needs, as I mentioned here, some application need some surface modification, and some doesn't. And most of the implants doesn't need surface modification. In some application only. And you know, surface modification, if you ask for dental doctor about the price, he say this one is equal to, for example, $1,000, and this one is $2,000 only because of the surface modification of the same material. So depending on the functionality and so on. So who will pay and what you will gain? It's a matter of your decision. But surface modification is very important, actually. It's a very good selling point for the commercialization.
Okay. Thank you, sir. Very nice session. Thank you.
Any other question? I have one question, Professor Gabriel.
Yes, please.
Just Dr. Vipin said that what method can be used to cast the titanium. So you have suggested an electric arc casting method. So
yeah. The important is the homogeneity.
But we need some inert gas environment to protect titanium in a casting process.
Yeah, titanium is active element, and the oxygen is very easy to go in. Oxygen, hydrogen, and nitrogen. So you have to make them in the limits.
Okay. So we need some sort of vacuum to cast.
Yeah, we have to do vacuum and substitute with argon.
Right. So any other question from the participant? Okay, I think there is no question from the participant. Actually, the presentation is itself very clear and new information is there. And the presentation is given in a very simple way, which is easy understandable to all the participants.
I wish it was like this.
Yeah. So it's a very simple and very informative actually. It is very easily understandable. So with Professor Gabriel, I have very long association. We have published various work and patents are also with Professor Gabriel. He is my professor, mentor, and collaborator. So yeah, we did a lot of work, and I have learned many things from Professor Gabriel.
Oh,
and still we are,
it's my honor and pleasure to collaborate with you always, Professor Sedhu.
Thank you. So yeah, with this session, concluding remark from my side, sir. Thank you, Professor Gabriel, for sharing your invaluable experience and insight and expertise with us in this FDP.
Thank you so much.
Your presentation has provided us a very wealth of knowledge and latest technology in development of titanium alloys, specifically for the low cost, good property alloys. So this is a very informative session, sir. Appreciate your time and that you have invested in preparing the lecture and preparing this slide. Very informative presentation, sir. Thank you,
so
sir.
much.
Thank you.
Appreciate it. Thank you so much. Wishing you best and very enjoyable rest of the training course.
Yes, sir.
Yeah.
So I
Okay,
request you, sir, you have shared the questions. I need the answer key of that questions also.
I already sent with the answer itself.
Okay, sir. Okay, I will check it.
Okay, thank you so much.
Thank you. Thank you, sir.
Yeah, very. Thank you. Thank you. Please.
Professor Sahil, can we proceed for the next session?
Yes, yes, Dr. Sidhu. On behalf of the organizing team, I would also like to thank Dr. Gabriel from Egypt for sparing your valuable time. Thank you so much, sir.
So, dear
Thank you so much,
participants,
Professor. It was my pleasure really to be with you today. Thank you so much.
Thank you.
Wishing you the
Thanks a
best.
lot.
It's very interesting for me actually. Thank you so much.
Yes, thank you. And now we proceed to our next session. Our resource person, Dr. Arnab Chanda, has already joined. Dr. Chanda, am I audible to you? Dr. Chanda, your mic is mute. Kindly unmute your mic.
I can hear you. Yeah. I think my video will also load in a few seconds. Yes. Hopefully you can see me. You can hear me. Good afternoon, everybody.
yes.
Good afternoon. Good afternoon, Doctor. Welcome to this FDP.
So before that, please allow me a brief introduction about Professor Arnab Chanda ji. So Professor Chanda is an associate professor in the Center for Biomedical Engineering, IIT Delhi, and a joint faculty at Department of Biomedical Engineering, AIMS, Delhi. He is also a founder of startup company BioFit Technology LLC USA. He earned his PhD from the University of Alabama, USA, and has been postdoctoral researcher at the University of Pittsburgh, USA. Dr. Chanda is an expert in the area of biomechanics, especially in tissue mimicking artificial tissues and finite element analysis, robotics, variable devices development, and entrepreneurship. To the date, he has received a Young Research Award and Award from ASME, MHRD, and AO Spine International Singapore, and top cited award from IOP Publication and Valley. He holds and has filed 10 plus US patent and Indian patents and authored 6 books, 100 plus articles in reputed international journal. Dr. Chanda is in the list of top 2% scientists worldwide as per the Software and Stanford University database in both the years 2023 and 2024. He also teaches 2 executive programs, executive program in healthcare entrepreneur and management, and executive program in robotics and multiple SWAM to engineering doctors, to engineers, doctors, and management professional. Dr. Chanda is serving as an editor of Biomaterials for Multifunctional Application, a book series published by Springer nature, and I hope this book is going to be indexed in a Scopus, a very popular book series by Dr. He is an editorial board member for the Nature Science report and guest editor for several journals such as Engineering Research, Express, IOP Publishing. So, sir, I welcome you in this session, and sir, may I request you to start your lecture, sir, please.
Thank you so much, Professor Sidhu, for the kind introduction and the nice words. Very much looking forward to the session. So I will probably just share my slides and get started. And thank you everybody for listening today. So,
thank you.
Just, okay. So optimize for text. Okay. So entire screen I'll share. I'm hoping my screen is visible. I am actually logged in not through the Zoom app. So if you could just tell me once whether my slides are visible in full screen. If you can see.
Your slides are visible very
Sir,
clearly.
it is visible and clear.
Okay, perfect. Thank you so much. Okay, I'll get started. So thank you so much everybody for having me today here as a part of this very innovative conference. So I've already been introduced. So I'm Dr. Arnab Chanda. I'm an associate professor jointly working with IIT Delhi and AIIMS. So today my lecture is going to be, and my talk is going to be on development, testing and applications of artificial human tissue simulants. This is an area I've been very passionately working for the past close to 15 years, and we have made quite a few interesting developments in this area, and I'm hoping that many of you will enjoy some of the results and what I have to showcase as a part of this lecture. Right, so getting started. Step one is, what is the need for artificial tissues? Why do we need artificial tissues in the first place? So there is a huge need for artificial tissues for realistic surgical training. So right now, even with all sorts of haptics based testing and testing medical models where we have lack of material properties, we do have the structure which we can construct using 3D printing, but we do not have the exact materials which the human tissues have, right, in these kind of structures. So it is very difficult to produce artificial tissues which have exactly the property of the native human tissue as well as having the structure. Right, and there is a huge demand in medical schools and hospitals for such kind of surgical training and simulation models. And cadavers and live human tests are very difficult to conduct. Of course, there are certain institutes which does conduct some tests on cadavers, but it's bound with a lot of ethical approvals, and there are limited things which we can potentially do. Right, and due to ethical and biosafety issues, if we could build an artificial tissue which we can potentially carry in our pocket, or probably just ship it to a place without having to worry about the biosafety hazards, that would be. Sorry, I thought I got it.
Attendance is the participant. Login karoge na?
So I think there is a little bit of a crosstalk. I think yeah. Thank you. Yeah. So that is the need for realistic surgical training and medical simulation where artificial tissues are needed. Further, what do we need in an artificial tissue? What we need really is the mechanical properties and the structures which is similar to the natural tissue. Structure, like I said, is easily recreatable, but like mechanical properties is something which has been missing for the longest time. And next is next layer of thing is surface properties. If we can achieve those surface properties similar to the natural tissue, it's on an it's kind of an icing on a cake. And third part is biosafety. We need to be making something which is biologically safe. We should not have ethical issues or approvals which are needed, because it takes a lot of time to really get those approvals and hampers research as a whole. And the last one is low cost price for countries like India, where we can actually build a simulator which is within a reasonable cost frame and not costing super high, which with limited accessibility, right? So some of the pictures on the right side showcase some broad interest areas with artificial tissues, like from building of artificial organs to usage of such artificial tissue simulants into prosthetics and orthotics, to using them for biomechanical testing, and also testing of a lot of cosmetic products, surgical simulations, and also for testing of high strain rate ballistics, right? So these are some of the applications out of many of artificial tissues. So the first issue I'm going to talk about is the artificial skin. So when I started with this work back in 2015, there was no surrogate or simulant, or whichever term we want to use, phantom, to date, which could mimic the anisotropic mechanical properties of human skin. Human skin is extremely anisotropic. If I pick out a skin from my facial region versus, like, having a skin from somewhere else, from the thigh region, it's going to behave very, very differently, right? So one is that, and second is, at the same region, if I look at skin from different directions and different orientations, the skin property again changes. So that being said, like, skin is extremely anisotropic. So nobody was able to come up with an anisotropic skin. So most of the commonly used simulants which were used in the market included porcine skin, cowhide, polyurethane, gels, or cadavers. Cadavers are, of course, like, subjected to tissue changes due to dehydration and so forth, like after a certain amount of time, once there is that after death, like typically 12 to 15 hours is the common time frame. After that, the tissue property starts to degrade and change, right? So given all these challenges, we wanted to create a material which could come in terms of mechanical properties as close to the human skin as possible. So if you look at this plot here, this is the property of the porcine skin, which is the pig skin, which is ideally considered to be a human skin simulant. So as you can well see, it is quite different in properties from the human skin. The human skin property is here. It's in the skin or the orangish color. And what you see at the bottom is gels or PDMS, these kind of silicon based materials which have properties much lower than the human skin. So none of them are good candidates to replicate human skin properties. So that is where we came out through a lot of permutation and combinations, and with a lot of research, with an artificial skin simulant which could behave as close as possible in a nonlinear fashion, where the stress strain nonlinear curves are almost matched within the given error bars, where we could call this as a variant of human skin. So this was the first time we were able to create this, and of course, with the industry demand, we had to package it in different forms and shapes. So this is a snapshot of some of the colors of the human skin which we created. So this is the US patent which was filed back in the day, and right now has been fully granted in 2021 after almost 5 years from 2015. And this is on biofidelic skin simulant, where we hold all the rights to the recipes and the secret composition of this artificial skin, right? Now the next component is that now we have the skin, what do we do next? Can we use it for some surgical simulation? Before we could do that, we had to make sure that to match skin properties, not only in tensile test or compression test, but also in an actual surgical setting, we should be able to develop something low cost and mass producible in that aspect. So we started doing some wound suture experiments. What we did was, what you see on the top is basically some cadaveric skin. So these cadaveric skins were tested, and we created our artificial skin, conducted similar wound suture experiments there, and wanted to compare how much force is applied, because this is exactly how a robot would actually conduct a surgical suture. They would go by the forces, right? If the forces are dissimilar between the actual human skin and my skin simulant, that won't work. So once we were able to optimize that, figure out the forces which are needed for surgeries, for sutures and whatnot, I started building a product basically out of this skin simulant material, which was basically built under my company, startup company, which is known as Biofit Technologies LLC. This I filed back in the US, and I was the founder of this company, where we created this nice skin patch. The uniqueness about the skin patch is it has 3 layers of the skin: the epidermis, dermis, and fat layer, all in 3 different properties demarcated by the colors. And what you see on the top side is a bunch of wound shapes. So you have different kinds of wounds with different spacing, and there is an aspect ratio to a wound. So we wanted to create some different wounds, and so that the surgeons or any medical trainee can basically practice on them. We also wanted them to go for some other options, like if they want to extract some molds or skin tags to get some exposure, because these were based on out of the market demand. So we created all the way from a skin simulant to a product at this time. So what goes in the backside is this: we ran a lot of experimental tests to create that very unique composition which we can call skin simulant. So what you see in this picture here is a range of compositions. We have basically captured test 1 to 23. This is just 23 out of hundreds of compositions which I've tested. What I did was, it was kind of a hit and trial method. So we started mixing different kinds of polymers and started getting some response, stress strain response, right? So what you see in the stretch in the bottom, the row basically, or the x-axis, is basically nothing but strain plus 1. It is just a quantity which is used for all kinds of hyperelastic model and other models, which I'll showcase like in the upcoming slides. So stretch versus strain, you can assume. Only difference being stretch is nothing but 1 plus strain, right? So we are looking at a stress strain response where we started from the very bottom and started going up. So once we made the polymer composition stiffer and stiffer, and parallelly what we did, we created some bounds for the skin, which is the human skin upper bound and human skin lower bound. These bounds correspond to the maximum mechanical property which the human skin can showcase versus the minimum property which the human skin can have all around the body. So our goal was to get a polymer which has properties somewhere between the upper and the lower bound. If we are able to get that, then we can consider it to be some form of skin. Whether it is forehead skin or thigh skin, that's a different matter, but we could have it some form of skin. So that was our initial test, where we were able to reach that platform through a certain type of composition. And one of the compositions which we identified was known as a 90-10 control specimen. 90-10 specifically referring to the composition ratio, which basically states that there is a 90% of one polymer and 10% of another polymer. This composition we selected specifically because this corresponded to the lower bound of the skin. We conducted a lot of repeatability tests and looked at the low strain and high strain modulus. What happens typically with non-linear soft tissue kind of material is we cannot model it using a single modulus of elasticity, because there is no single line which fits the curve. It's a non-linear model, right? So what we do is we usually use something which is known as a hyperelastic curve fit model. But another thing which we can do is we can drop a tangent from the very top and drop a tangent from the very bottom to the curve, and we can call them low and high strain modulus. So we wanted to compare the low and high strain modulus of this simulant material with the actual human skin. We also tested on ultimate tensile stress, right? And we looked at whether the nonlinear behavior was similar, and we were able to optimize all this, right? There was repeatability, there was reproducibility. One thing which we did notice was the way the skin simulant breaks or damages is very different from how the skin damages, human skin damages. The difference being due to because skin has fibers and this particular simulant doesn't have fibers. It's based out of an isotropic kind of material. So we are trying to simulate anisotropy with an isotropic material. So that is where the disconnect was, but still we were able to do the job because we are able to have a nonlinear property which nobody was able to match so far. So this was the first artificial tissue which we had created, and we got really interested and we started diving into the area, this particular area, and we started creating artificial tissue mimics for a lot of different kinds of tissues which are of medical simulation interest. So this is the second tissue. We created an artificial artery. So artificial artery, the motivation was if there is a stent which needs to be placed for opening a blocked artery, the stent has to be rightly sized for an artery. What we get in the market is a standard size stent. So can we have an artery simulant which we can create out of medical imaging and then incorporating the mechanical properties, where we can place a stent before we actually put it in some person, like, or some patient, where we can test whether the stent sizing is right. Because if the stent sizing is smaller than the arterial lumen dimension, which is the internal dimension, then basically what is going to happen is the clot will not open up properly. The blood flow cannot be proper. And if the stent is oversized, then it will scratch the surface of the artery and it can create thrombosis, right? On tissue ingrowth within the stent, which can create additional problems like further clogging. So we wanted to get the right size stent, and that was the motivation. So we started creating this artificial artery model, and this is of course difficult to create. It's not something which we just pour in a mold, right? So the way we did this was like we collected a set of MRI images and converted it into a model. We 3D printed this model, which served as the model of the lumen or the internal hollow part of the artery, and we grew the artery in layers on top of this lumen. The way we did this was there was a technique which I had invented, which is known as time control dipping. So we make a polymer mixture and we time it. After a certain point, when it has polymerized a little bit, we dip it and pull it out. That provides a particular thickness to that layer, because with the artery, the layer thickness is very important. Of course, I can replicate the property, but the layer thickness has to be accurate, because there are 3 layers, namely intima, media, and adventitia. So what you see in the top is the range of polymer compositions which I have created. It's a little blurred out because I had a lot of information here, and we have compared those ranges with the upper bounds and lower bounds of mechanical properties of each one of these layers, right? So we got the mechanical property and we got the structure. So finally we were able to create an arterial a model which has mechanical property. Each layer has mechanical properties same as the human artery, each one of these layers, and same as the human size with the right structure. So this is how we were able to create an artificial artery. This was the second soft tissue which we created. Another soft tissue which was of interest was the artificial brain. We saw there were a lot of research which is conducted on the artificial human brain or cadaveric brain, relating from blast testing to ballistic testing. So we wanted to create some tissue materials which can replicate brain tissue properties. Of course, brain has 2 types of tissues. One is gray matter, one is white matter. So we started creating a property matrix for the gray and white matter, and we created 2 different polymer sets, one for replicating the gray matter, one for replicating the white matter. We tested them in tensile and later in compression. And we also tested them at different strain rates, just to make sure that sometimes there can be an impact to the brain due to a certain vehicular accident or due to a blast. What happens with the tissue with such a high strain rate? Even though we could not go to a very, very high strain rate, but it was still like comparable. At least we could go to some ranges of strain rates. This is the next step of things. Once we were able to basically streamline the brain mechanical properties with an artificial tissue composition, next step was we wanted to put a structure on it. That brain tissue property is okay, but what about the brain structure? So we did MRI based scanning, and based on that we got a brain structure. What we did next was we took that brain structure in a CAD model. We created a box around that brain, subtracted that brain out of it, and broke that box into 2 parts. We cut it out into 2 parts and created some pegs and holes, so that now I can print this molds. So these are the 2 molds, A and B. These are the designs of the molds, and this is the final 3D printed mold. And what you see on the right side is actually the molds with the pouring. So basically, having worked in this area for a while, I knew how these polymers would exactly mix. So I poured them and let them stay there for a while, because if I flip one on top of another, the material will come out, right? So I wanted them to polymerize a little bit, and I had to time it properly. And once I could time it properly, I flipped the other part on top of it, and the peg and hole made sure that it is properly aligned, right? So I let it cure for a while, and finally the brain model which I get is a properly adhesion, well adhesed like brain, like which is this one, where you cannot really demarcate the you can see the line faintly, but you cannot see much. It is properly integrated. So this is the brain model which we have created, which doesn't only have the mechanical properties of the actual brain, but also of the structure of the actual brain. So this was the fabrication of a full-scale brain model. Now what we did next was we put the brain model in a UTM and tested the brain model in different directions, different orientations, specifically to replicate that what if there is a fall of some material on the brain, like people wear helmets and there is some impact on from the top of the head, then this is the model to look at. If there is a frontal impact, then this is the model to look at. If it is side one impact, this is the model to look at, right? And we started running tests, and also at different strain rates. As you can see, we could go from 25 millimeters per minute to 300 millimeters per minute, which is not super high, but at least will replicate some impact condition. So this was mechanical testing of full brain model. So we got a bunch of results. Where we got the load displacement plots, and finally the load displacements were compared across the strain rates, and we found that there was not a huge change with the strain rate per se. So this particular material model which we had of polymer did not see a huge variation of strain rate effect as a whole, but like we did see that when the impact orientation was changed, or the test orientation was changed, like the load displacement plots typically change, they move from top to bottom. So orientation 1 is what we are looking at. This is the orientation 1, where uh, top portion of the parietal lobe like is basically compressed, orientation 2 and orientation 3 and so forth, right? Next material which we wanted to create. So basically if you look at it, like we are creating a lot of materials for different applications, and I'll get to the point how they have been used in the application. The reason we went so diverse was because we had realized that we had created a material which is a standard material which we can quickly change the composition and use it for replicating a lots of tissues. Our goal here was to have a first mover advantage in the market. We wanted to create all these kinds of materials and structures with it, so that tomorrow I can potentially create a artificial cadaver or a particularly artificial simulation model which has a lots of these tissues. We did not want the other parts of the market or other companies to come in and create this for us, like using our material. So that's why we went it so diverse and we started creating so many models. This is another model where we created an artificial normal and disease calcineal fat pad model. So calcineal fat pad is the bottom fat pad of your foot, which basically gets degraded over time, and when you walk a lot and you are into athletic activities and things like that. So we created a fat pad replica with the same material properties and with the same structure. These circular almost cylindrical specimens describe the same measurements as the calcineal fat pad. So we conducted a bunch of compression tests, and we created a matrix of tests not only for the normal fat pad condition but also for disease fat pad. Like people with diabetes have a very different kind of fat pad where the material has stiffened up, and people with plantar fasciitis, patients with plantar fasciitis also have a different fat pad. So how am I going to use this particular fat pad tissue? One is for biomechanical testing. Second is I could use such artificial material in an insole to substitute for that damaged or lost fat pad which a particular person is encountered. So if you look at the graph at the bottom, we are basically created a bunch of compositions which are complying to the healthy control plantar heel pain kind of group with a certain kind of fat pad properties which have been declared in literature, and diabetes group which are a different kind of fat pad properties. So we created not only artificial tissue mimics for the natural tissue or the normal tissue, but also for disease tissue for the very first time. We did a lot of cyclic loading and unloading cycles because many of these tissues undergo a lot of loading and unloading cycles. They are not a one-time loading like the brain, which can get hit once, right? So foot gets usually, like loading and unloading is happening like all day through, like while you're walking or running. So we did some cyclic tests to compare the cyclic loading and unloading force displacement curves, engineering stress strain curves, and also looking at what is the effects of strain rate. So strain rate had a clear effect on these compression models, but we could compare it well with the literature, as you can see on the plot here. So the surrogate versus the healthy control showed a very similar kind of pattern. Of course, there is some energy relaxation which components are little dissimilar, but like overall within the error bars it was coming out to be somewhere close. We were able to optimize the material properties, and by the way, we were able to optimize this not on one go, but this is almost like on 50 goes, after which we have used a lot of different compositions to get to this point, right? So this is a quick intro into all sorts of some of the many artificial tissues which we have created. After this, we have gone into the directions of creating a liver tissue surrogate, gallbladder tissue surrogate, eye surrogate. So mostly if anybody is interested, you can look at my profile of particularly the papers, and you will be able to see a lots of these surrogates and simulants and so-called phantoms which are there for lots of different applications which we have been able to create using these material recipes. This is just to give you a snapshot of some of the artificial materials. Next topic was, now that we have been able to create some of these structures and with the properties, how do we use some of these models in computational modeling? Because many of the scenarios, basic UTM based compression or tensile testing is fine in a UTM, but an actual injury doesn't happen like that. Actual injury may happen while I'm sitting inside a vehicle and there is a vehicular crash and my head hits onto the maybe the windshield and there is a fracture and there is a rupture in the brain. So how do I model all that? So for that, I have to go to the finite element modeling. I could use the properties of the material, but next part is finite element modeling. So how do I do finite element modeling? I have to take the mechanical properties and characterize the mechanical properties of the soft tissues in order to use them in the finite element model perfectly. So that is my second part of my research, where we did mechanical characterization. So we started off with something which is known as isotropic hyperelastic model, which is widely known and used in the industry. What it does is, typically the theory is on the left side. You're basically looking at a simple isotropic model. If you apply a stretch of lambda, then it gives the same response. So same stress strain response on all the directions. So typically isotropic hyperelastic model is given by the definition of material strain energy function, which is given as psi, which is a function of the invariants 1, 2, 3 of the left Cauchy-Green tensor in continuum mechanics. So left Cauchy-Green tensor is the one which depicts the properties of the material, and I1, I2, I3, the function of this is defining the psi, which is energy, material strain energy function, sometimes also known as material strain energy density function. So out of this, I1 is given by sigma of I bearing from 1 to 3, like lambda I square, and then I2 is lambda I lambda j whole square, and I3 is a product of lambda I square. Finally, we apply stress strain relationship to it, like, which is a set of partial differential equations. So what are the isotropic hyperelastic models? If you look on the right side, psi is your strain energy density function, I is the material invariant, this lambda is the principal stretch. So if you remember in my equation, in my plots, I have the strain versus stress versus stretch, rather the stress versus strain. So stretch is this lambda. Lambda is nothing but strain plus 1, which is epsilon plus 1. So these are the hyperelastic strain energy functions which have been created by different researchers, like Muni-Rivlin has created back in the day, which is more of a polynomial function. Then Veronda Westman has come up with an exponential function. These are nothing but essentially curve fit equations. These are basically curve fit equations for basically modeling the mechanical response of a soft tissue, which is nonlinear in its sense. Then you have Humphrey model, Yo model. These are some of the many models which are there into the market. Then how do you get the hyperelastic stress strain relationship, which you can actually use in the mechanical characterization? That is through partial differential equation and application of the uniaxial test condition, which is sigma 2 and sigma 3 going to 0, and lambda 1 is equal to sigma 1 is equal to lambda 1 dou psi by dou lambda 1, which leads us to these equations at the bottom. So sigma Muni-Rivlin is given by 2 times lambda square minus 1 by lambda whole C1 plus C2 1 by lambda. So that typically states there are some variables, C1 and C2 are some constants or variables, like, which are there, which are basically known as parameters of the hyperelastic model parameters. And the equation is between sigma and lambda. So whenever I get an experimental plot, I get stress, which is sigma, I get strain, which is epsilon, 1 plus strain is this lambda. So if I can model that stress strain data within the system, I will be able to figure out the value of C1 and C2, and that will define that this is my hyperelastic property C1 and C2. Typically have a unit of megapascals, right? So Veronda Westman, again, this is the filtered equation. Humphrey model, again, this is the filtered equation. And then another one is the Yo model, which is another filtered equation, which is a little longish equation. So in some of these equations, we see more parameters than less, right? So typically an Excel, Microsoft Excel curve fit solver is good enough for solving these kind of equations. Like typically what we do is we have the stress strain property from the actual experiments. Then we assume that C1 and C2 is something like maybe 1 or 2, something to start with. Then based on that, we use this particular equation to back predict what is stress. So by substituting lambda from the original experiments, we back calculate sigma, which is of course not true because C1 and C2 will not be the right, and we come up with a predictive column, and we take a subtraction of that predictive column and the actual column, which is the actual result, and subtraction and whole square of that. So that is, and then add everything up, set it to the minimum. So summation of all the square of differences set to minimum, that will, and if I set the solver add in this kind of operation, it will automatically curve fit and give me the value of C1 and C2, which will tell me that this is the property of this particular hyperelastic material. So this is what an isotropic hyperelastic model looks like. And I've been able to apply this for lots of my tests, like, like anybody else, in most of my skin tests and like, all sorts of like brain-based medical tests, like those things we have applied. The next kind of hyperelastic model is known as a transversely isotropic model, where what is happening here is, rather than having a completely isotropic model, here there is a contribution of the fiber, but there is no interaction of the fiber which is modeled with the matrix. So in a composite kind of setting, as if there is a contribution of the fiber, like overall contribution, but there is no particular interaction which is modeled. So here typically the psi, which is the material strain energy function or strain energy density function, is broken down into psi of matrix plus psi of fiber. Psi of matrix is given as one type of isotropic hyperelastic model, which was the previous model, and fiber is another type of isotropic hyperelastic model. Now when we blend this two into the system through a bunch of like derivative steps, like where you can see there is a deviatoric component, trace of a matrix, right? So there are lots of operations in continuum mechanics which we use, and finally when we apply the uniaxial test condition, what we get is a transversely isotropic model formulation, which is again a model of with sigma and lambda only, with a bunch of C1, C2s and so forth. So all the equation boils down to is this equation between sigma and lambda, which we can again curve fit our experimental data with. Just the number of parameters have gone up, right? Here it has the contribution of the fibers. Now the next step was, this is my model where I have been able to come up with like a novel anisotropic soft composite model, because if I'm using an isotropic model for soft tissues within a computational model or FEM model, it is not going to do the job right, because if my brain gets hit from this direction and the property which is experienced like in this direction, if that is same as the orthogonal direction, then it's a problem. Some level of anisotropy has to be included. So that is where we started with a novel anisotropic soft composite model. There is a paper on that, like which we have written back in 2021. So this model, the way it works is, it doesn't only look at the fiber presence like within the system, like it has a fiber and a matrix, but also models the fiber matrix interaction. So that means when the entire material is stretched by a particular amount, the fiber rotates by a particular degree, right? So the fibers, let's assume initially are aligned at any degree, or could be aligned completely towards the direction of loading. So they rotate to describe the interaction between the fibers and the matrix, right? So based on that, the model becomes much more complex. The psi becomes the material strain energy function becomes a function of the C and the A naught, which is a function of basically I1, I2, I3, I4 and I5. These are lots of invariants which are part of the equations. Not getting into those details, but then what happens is, next is we assume the property of the matrix as one type of isotropic hyperelastic model, and the properties of the fibers as another type of isotropic hyperelastic. And then we do a bunch of operations of rotations and whatnot, which are basically all kinds of like permutation combinations with matrices. And finally what we get is, we also define the fiber matrix interaction using it, which is basically using a whole composite decomposition method, multiplicative decomposition of the system. And we also involve the contribution of the fibers, that how much fibers are there and how much matrix is there. Because there can be certain tissues which has more fibers, certain tissues which has less fibers. Also with aging, the amount of fibers decreases. Somebody with a wrinkling skin in their 60s or 65 would have less collagen in their skin as compared to somebody in their 20s. So that is where the matrix and the fiber matrix fiber contribution comes into the system. So we modeled all of this into this soft composite model. We also included the effect of, you know, the fiber stretch, and we modeled all these equations. I'm not getting into all these details because there are a lot of derivation steps. But long story short, what can be done is there are lots of models to start with. So our starting point is selecting an isotropic hyperelastic model, which is already defined by many researchers earlier for the fiber, and a similar isotropic hyperelastic model for the matrix. So matrix is isotropic, fiber is isotropic. When we blend them, that creates the anisotropic. So we blend them and we create this range of equations where we are able to depict the anisotropy. And we also include fiber matrix interaction and fiber matrix contribution. Finally, we also introduce the effect of fiber orientation. What if the fibers were initially aligned at a certain degree from the direction of loading? That is quite possible, because whenever we take a piece of skin or piece of the brain, like the fibers may be aligned in any direction. It depends, like wherever the impact is, the fibers may be aligned off of it. So what happens due to that? So we introduce those theta effects as well, where it's a very simple equation, lambda f is equal to lambda cosine of theta, and that we incorporate into our equation. So we end up with this large equation where sigma 1 neo-Hookean modified 2, I'm calling this, right, is equal to twice of something something, where nu m is nothing but it is the matrix volume contribution. So nu f is nothing, fiber volume contribution. Nu m plus nu f is equal to 1, right? So C1 and C2 are the parameters. Theta is the initial direction of the fiber, right? And out of this overall equation, what I'm really putting my experimental data is into this sigma and lambda. So it's again a sigma lambda equation with a bunch of parameters. Now, one thing to keep in mind is, how do I know that what is the fiber composition in a tissue? Another question is, how do I know the fiber orientation in a tissue? So there are two methods which are typically used to look at fiber orientation. Typically what is done is you basically look into the tissue by doing a microtome. You do a microscopy and you basically look at what is the fiber orientation, or in certain cases, like you could look at the tissue like we did for the human heart. We basically opened the heart in such a place like the entire heart kind of unwrapped itself and we could see the tissue structure. So visually most of the tissue structures can be seen. Otherwise you can use techniques like DT MRI, which is diffusion tension tensor imaging like of the MRI, which can basically use water particles to look at their deflection and look at the fiber orientation, DT MRI imaging. And the other component is like the fiber volume fraction. How much fibers are contained in this tissue? So you have a piece of tissue. What you need to do is you cut it, microtome it, orthogonal to the direction of the fibers or in a particular direction. Every slice which you have, you calculate by using imaging that how much are the collagen fibers area wise and how much is the overall area. If you take that ratio, that will give you the fiber area fraction in that particular slice. If I take an average of that across all these slides or multiply it accordingly with the length, I will be able to get the fiber volume fraction. So that is typically how these numbers are put. So it's a very multi-dimensional, multidisciplinary kind of research which comes into the picture. We are able to use all this data. So all this is predefined. The fiber orientation is predefined. Fiber volume fraction is predefined. So again, the equation boils down to, we get experimental data, stress versus strain. We can model it using this equation with all other predefined parameters, right? So finally, we could come up with this model, which is the most advanced model in hyperelastic modeling, which is known as the novel anisotropic soft composite model. What we have done is, we have not only considered the effect of fiber matrix orientation, the fiber matrix interaction, their volume fraction, but also the effect of different layers in which the tissue can be, with different layers of fibers. Like for example, the human heart tissue comes in two levels, two layers. One layer has a certain type of tissue structure, fiber structure. Another layer has a different type of fiber structure. So what if a tissue has multiple layers? Skin is again multiple layer, 3 layer. The epidermis doesn't have too much of anisotropy. Dermis has a lot of anisotropy. So we came up with a model, composite based theoretical model, where we are able to look at this anisotropy. So what this model considers is, this model assumes that the soft tissue has multiple layers. Each layer has the same fiber, same matrix. The only difference is the volume fraction of the fiber is different in each layer, and the orientation of the fibers are different in each layer, right? So the difference in each layer is by the virtue of only the direction of the fibers and the fraction of the fibers which are there, volume fraction of the fiber. So this is the model which we came up with. So finally, when we add all the strain energy density functions together, so so this is the final equation, how it looks like. If you started with a neo-Hookean type of model, isotropic hyperelastic model for fibers and the matrix separately, then this is what you end up as the equation with an anisotropic soft composite model, incorporating the effects of fiber orientation, fiber volume fraction, and the fiber matrix interaction. If you started with a Humphrey type model, the model becomes even longer because the initial starting equation was quite large. The assumptions for this model are the soft composite has n fiber matrix layers. So we have started calling a tissue or a soft tissue as a soft composite here. So it has n layers of fiber matrix layers or laminates. The mechanical property of the matrix and fibers in each layer are assumed to be the same. That means the C1, C2 do not change. C1, C2 stays the same, only the layer wise things get added into the equation. That's all. The layers are assumed to be perfectly bonded. This is one assumption. We have not looked at any kind of play or possible friction between the layers. It's a completely bonded layers. That is what we have assumed. The interaction between the layers was not modeled. Any kind of frictional interaction, or if there is an interplay between the layers, that was not modeled. But still, with these assumptions, of course, every equation comes with a set of assumptions. We were able to create a model which can basically, now any soft tissue which you pick from the human body, I can fit in this model with some microscopy, with some fiber orientation understanding. If I fit in this model, this will give me the equational parameters. Now if I use this in a finite element model, I will be using tissue properties which are the most superior as compared to any other isotropic model. Most of the finite element models, if you look into the market, are using either a normal modulus of elasticity and a Poisson's ratio kind of definition, which is absolutely not correct, because these are non-linear tissues. These do not have a linear representation of stress and strain. And second is, using isotropic hyperelastic models are not right because they have anisotropy, right? So this model, if we can use like in a finite element model, this would be a worthwhile characterization model to use. So we have started using this right now. So the third component which I wanted to talk about, and this is probably the interesting and exciting part, is the surgical application. So how do we now start applying some of our work into the artificial tissue development and material characterization into surgical application? So this is the first application where we have started looking at soft tissue damage and repair. So both in surgeries, like where we want to create a suture, or I'm trying to do a surgery. Let's say I want to reach out to a particular section in the body where I want to create a cut or a wound, create a particular shape so that I can reach out properly to that particular organ. I don't want to create a huge hole there and go inside, right? So what kind of cuts should I create which are minimally stretched and which can be easily sutured back and repaired to normal? That is one of the very important points which a doctor looks at. That can I create some cuts and incisions which are so small and so strategically done so that I can reach out to an organ and quickly suture it and they will repair on time. So that is the first thing. Second is, if there is a wound and I want to repair it using some surgical practice or robotics, what is the right amount of force? How much should I apply on the sutures? How many sutures should I place? Nobody has this equation. Nobody has this optimized number. Surgeon knowledge usually is like something which drives that. Somebody with a 20 years of experience sutures in a very different way. Somebody with a 5 years of experience sutures in a very different way. So how do we make a global standard or some kind of a standard where everybody knows that if I see a wound of this shape and this size or this ratio, in aspect ratio, I should make 5 or 10 sutures and this type of sutures. So that was the motivation for this research, which is the next, which is into the wound suture closing. That is where we applied our artificial human skin for the very first time. This is talking about the applications of what we have created. So we started creating different kinds of wound geometries and microscopically looked at all these wound geometries, which are presented on the right side. You're looking at long and short wounds, top, center, and bottom wounds to the specimens, and we created interrupted sutures. So what we did was we had a tissue phantom or a artificial tissue model. Next part was we created a wound. Simple kind of scissors or some kind of scalpel can be used for creating these wounds. Next is we suture this wound, and we wanted to see what is the property of the skin or property of the tissue due to the suturing. Is it the same? So that is something we wanted to find out through this research as a baseline research. So what we found out was through interrupted sutures, and we also applied some hyperelastic relationships for material characterization to understand what is the property of the material baseline with the wound, with the suture. This was never characterized before. Nobody has looked at mechanical characterization of tissues with sutures, right? So this is published as a part of the proceedings of Institution of Mechanical Engineers. This is known as Journal of Engineering in Medicine. This was one of the studies. Okay, so here are some interesting trends which we found out. So the first plot here showcases that when the tissue is not ruptured, the tissue property is something. When the tissue has a wound and different kinds of wounds, the overall average tissue property is lower than that, which is fairly intuitive. When the tissue is ruptured, the overall property of the material degrades like any other material. Now, if the tissue is sutured, there is some interesting trend which happens. The property of the material actually goes above, the average property of the material goes above the standard material property of the skin itself. This was a very interesting finding. So what we found was, if somebody over sutures, the skin is going to be overstressed. That being said, a surgeon needs to be careful that how much is the amount of suturing do I do? What is the optimal amount so that I'm not overshooting the stress strain properties of the skin or the native tissue itself. So that is what our first state of research found out, that whenever you over suture, the overall property goes above the property of the native skin. This was an interesting find. We looked further. We wanted to use all a very key imaging technique which is known as digital image correlation. I'm sure this is used across lots of material testing, and many of us know what this is. What I'll still explain, like just to keep everybody in the same page. Digital image correlation is a technique which is used as an experimental technique where we apply a spray pattern to a particular specimen, and we basically conduct a normal UTM kind of test, and we understand and we take a video of this entire test, and we then process it through a DIC kind of software. The goal here is to look at how each particle or each speckle, we call them, each spray particle is known as an irregular or a clear speckle, how these speckles are displacing with respect to the initial position. Initial position is at the state of rest, right? How are they displacing over time? Why is this information useful? Because based on this, I'll be able to make a strain field mapping on this experiment. That is my only way of comparing a finite element model result with an experimental result using DIC. Because I'm doing something with my experiment, I'm doing something in my finite element model. How do I know my finite element model results are correct? If I change a small model parameter a little bit, the finite element model will give me some other result. So the way to make sure is, when you get the finite element results of stress and strain or the strain distribution, you compare that with a DIC based imaging modality where we have been able to look at the strain field distribution. So the way we have done this is, we looked at the wounds, we created artificial human skin. Again, this is where this was very useful. 10 test coupons. We used irregular speckle patterns. We did videos imaging. 20.1 megapixel Sony camera was used. We used a free software which is known as VIC 2D by Correlated Solutions. We did some calibration and image processing, and we finally also determined an aspect ratio of the wound so that we can at least objectively quantify, and aspect ratios are written here, AR of 0.2, AR of 0.16 and 1.4 and so forth. So what happened next? This is what you get out of digital image correlation. A kind of a strain field image where the entire strain distribution based on the speckles or the points, how they are distributed across the surface of the particular specimen. So this is what we got out of the digital image correlation with this wound geometry. So what is the goal of applying digital image correlation in this particular application of wound geometries? The goal here is to understand that are there locations where there is extreme amount of strain build up, followed by locations around it where there are low strains. Those are the places where skin or tissue may rupture very easily. That being said, like, just to give it a context, if you have applied a suture of, or if there is a wound on a particular location of the body, there is a natural tension of the skin which is pulling the wound from all the directions. If the wound is in a particular shape, it has a chance of potentially propagating in its shape or becoming larger unless there is an intervention like suturing which is done. So when to do an intervention of suturing, when not to do. Typical understanding of the doctors is whenever the wound is based on a certain aspect ratio beyond a certain size, you go for suturing, because otherwise the flaps won't close. So the goal here was to give an objectivity to that scientific knowledge, that now we know large wounds have to be closed, small wounds doesn't have to be closed, but what do we mean by large and small? This becomes even more important when we are looking at skin grafting applications. When people have come with huge burn wounds where you need a lot of skin to be placed in those areas, like where the wounds are large, or you are trying to create a surgery where you need to reach an organ which is very much deep inside the body, right? So what should be the right shape of that wound? What should be the right shape of the incision so that it doesn't break out? So very interestingly, what we found out was, just look at this set of pictures here. Frame 1, t is equal to 2 seconds. Frame 8, sorry, t is equal to 24 seconds, and frame 12, 57 seconds. What are we looking at? We are looking at a little bit of curling which is happening on one of these sides. So initially there was a certain type of strain field relative colors, like this color map that changed, and after a certain while there is a region of redness which we see, which clearly states that is the region of high strain buildup. High strain buildup in that area means that is the place in which the rupture is going to happen. And interestingly, that is where exactly the rupture happened during our test. So this is how, using some imaging techniques and just by looking at certain wound geometries, we will be able to figure out that if this wound is in particular type of tissue, let's say this is in an abdominal tissue or skin or heart tissue, is it something which is you have to be really be scared of or be concerned about, or is this something which is okay? Through the simple DIC kind of imaging or some kind of observational imaging, you should be able to find out this information. So we wanted to send that benchmark, that what wounds are vulnerable, what are not. So this is where the application of the research lies. Also, this method allows us to track the strains in particular points. We also wanted to pinpoint in this 4 edges and see what are the strains, and very nicely it can be seen that P1 is the location in which the maximum strain is located. And of course, we can see P1 here where the curling is happening, right? And tearing was observed and tissue curling followed by tearing. So this is the interesting application in which our artificial skin development has really served its purpose, right? Next is another application which is into application in medical device testing. So there are loads of applications which I've worked on, like from wounds to skin grafting and so forth. But the next application is into the medical device testing. So whenever we say medical device basically comes in contact with some tissue, right? So we are going to take an example of one type of medical device tissue, like where hernia mesh is considered to be a medical device. So what is hernia? I'm assuming like everybody knows it, but just to kind of reiterate, hernia is basically whenever you have a soft spot in some place in the abdominal region, typically soft spot due to an accident or due to some injury, and due to the soft spot, an organ tends to protrude and come out of the soft tissue there, and it creates a very, very painful scenario. So out of the body's fat and the internal component, an organ kind of protrudes out. That is known as hernia. The way to control hernia, the standard practice in the market is they use something which is known as a hernia mesh, which is basically a polypropylene material. It's almost similar to what you see in lots of other meshes or medical devices. Polypropylene meshes creates a hammock. So what is done is this organ is placed inside and a polypropylene mesh is placed on the top. There are range of sutures, as you can see in the schematic picture on the top. So this is the case scenario of a hernia, right? And what you see on the right side is basically a set of sutures which has been placed by placing the prosthetic mesh here, right? So prosthetic mesh has created a hammock which will not further allow the organ to hopefully come out. And then you place the sutures and hopefully the organ will stay in its place and you will be okay. But the problem here is close to 20, we are looking at almost 602 crore hernia surgery, repair surgeries happen every year. Hernia surgery with prosthetic meshes have a lot of issues. You can look up hernia meshes in the market. There is another similar mesh which is used for pelvic organ prolapse, which is a female reproductive issue, which is a very similar kind of mesh setting. There are lots of lawsuits which are happening because these meshes are failing. So how are they failing? There are different modes of failing. One is there is a lot of pain and infection, which seems to be more of a biological issue. Pain and infection due to material mismatch. The mesh is not getting accepted or it is not highly biocompatible. Even though the material is biocompatible, the body is rejecting it. So pain and infection is a common occurrence. Hernia reoccurrence. This is more of a loading issue where the mesh is not able to arrest the hernia, and some way or the other, like the hernia finds a way to come out or protrude out of the material, right? That is known as hernia reoccurrence. This is a very common issue. The third one is mesh contraction. Mesh contraction, how does it happen? Mesh is dealing with soft tissues. Mesh is interacting with soft tissues which it is sutured with. These soft tissues are in motion. Our abdominal area and most of our muscles and tissues are in motion. We are eating, there is filling of the body, we are doing so many postures, so they're in motion. So there is a possible mesh contraction due to pulling of this hernial mesh from different directions. So it's a multi-axial loading, right? Last one is a mesh failure, which is again a loading issue where the mesh itself has failed. So something as mesh has broken down, the strands have broken down, or mesh has moved to a side and the hernia has come. So these are some common occurrences. Now out of these, biological issue is something which we cannot solve because we are not experts in that, but the loading issue is something which I can address. So what we looked was, we started looking into the literature. We started looking at why are the studies not effective in creating a hernial mesh which is able to basically confirm this loading issue and make sure that loading is okay and the hernia doesn't come back. So the first thing which we saw is there are lots of mesh biocompatibility studies which have been done in animal models, not in human models. That is the first issue. When you're testing something which is kind of a soft tissue challenge in an animal model versus a human model, animal soft tissues are extremely different, which I've shown in one of the previous plots, from the human soft tissues. So if you're testing a medical device in an animal model and implanting it in a human model without testing it further, that's the issue number one. Issue number two is dry and wet mechanical test. All mechanical tests which are happening in the market is with respect to the polypropylene mesh itself. So what they do is they put the polypropylene mesh in a UTM, stretch it and see what is the limit, whether it breaks or not. Second is they do a biaxial testing where there is a planar biaxial tester. They pull it from both the sides and test whether this mesh is okay. What is the limit beyond which it is breaking? But what they're not testing is their interaction with the tissues. So there, the literature gap which we found out was lack of mesh and human tissue interaction test. Now, how do I do this? I cannot place a mesh inside a human and say I want to test it inside you, whether something happens or not. That's not ethically right. So that is where my artificial tissues come into the picture again. The reason here is the lack of human tissues. I cannot use the human tissues ethically. So that is where I come back to artificial tissues. So using my artificial abdominal tissue, now I've been able to create an abdominal tissue phantom, which is quite easy given my different, recipe. So what I did was I created a mesh tissue suture experimental model, where what I did was I purchased this mesh. This is what the real mesh looks like. This is a hernial mesh. Okay. I also looked at the microscopic structures of this mesh, and this is a mesh which has been developed using knitting. We can very clearly see this is the microscopic structure of this mesh. I wanted to create the mesh microscopic structure in a finite element model too. So what you see on the right side is a finite element model. Of course, the scales are a little different. What you see on the left side is a experimental model. I wanted to see in both what happens in an experimental model due to the soft tissue and mesh interaction, and what happens in the finite element model due to this interaction. So I fabricated a pelvic tissue surrogate, which I said, phantom. I sutured the prosthetic mesh with the tissue surrogate. Next is I created a computational model where macroscopic prosthetic mesh imaging and repeated unit identification was done to recreate that model. Right? Development of a geometric model of the mesh, which is known as Proline. Proline is a very, it's an industrial mesh, which is given by, I think, Ethicon. It's a company which sells that mesh, right? Next is computationally suture mesh and tissue. So these are computationally sutured. So computationally suturing something is not very easy. You have a model. So in a finite element model, I'm not sure whether the audience is very well versed in finite element model, but I'll give you some examples. Finite element models, the way it works is you have a model, the computer doesn't know anything. You have a structure, you give a material property to it, you add some loads into it, and that gives you some results, right? Based on some equation. So that is what a generic finite element model is. When you want to devise an interaction between two models, like for example, the human tissue, the yellow part is the human abdominal tissue block representative. The other one is the mesh. When I want to create an interaction between the two, I need to use something which is known as a contact pairing. But this interaction is not straightforward in a suturing condition. It is through a suture. So it's not like the tissue is glued to the mesh. It is connected with a suture. So we have to kind of computationally suture something where you can see the half suture here. This is just for depiction. Half suture in which the suture has been bent and closed in such a way and then pulled from both the sides. So this novel technique of computational suturing was started, and we were able to create this computational model. Next story, what did we do? We mechanically tested across different strain rates. We tested it across the strain rates of 150 and 500 millimeters per minute, low to high strain rates, because many of the times the abdomen can get expanded or contracted at a very high strain rate versus low strain rates. It depends. Individual component tests were done. I cannot do an individual component test that easily in general, but here I could do using mechanical testing. So individual component testing means I did a tissue phantom test, I did a suture test, I did a prosthetic mesh test to look at what are the baseline properties of each of these three components and the overall composite, which is the mesh, tissue, and the suture, right? So I conducted mechanical tests on both these aspects, which is beyond what the industry does. The next thing is I look at the experimental results. So what I found out was some very interesting trends. The global mechanical properties means the overall mechanical properties. Of course, in a UTM, I cannot see what's happening inside. It's the overall property which the machine senses, right? So the global mechanical properties were identified. For stretch or strain, which is less than 0.5 or 1.5 is the stretch. Okay, so less than 1.5, which is 50% straining, the tissue was found out to be the major load bearing component. So what am I saying? Tissue, mesh, and a suture. So till 50% stretching, what I'm seeing is tissue is the major load bearing component. Beyond the 50% stretching, the mesh becomes the major load bearing component and undergoes a permanent deformation. Permanent deformation means it is not able to come back to its original form. And we found Eureka, we found that this is probably the issue with the meshes. This is how probably some of the meshes are failing. because nobody is testing it with the tissue. They're just testing the mesh, and of course the mesh itself has a limit and things like that, but they are not seeing the transition where the tissue is loaded first and then the mesh gets loaded, and then it undergoes permanent deformation. Also, another thing which we saw was prosthetic mesh twisting was observed along the loading axis. So the mesh and tissue, just because they have mismatching mechanical properties, one is a much more stiffer material, one is a softer material, there is this rotation when something is getting pulled because of mismatch of material property. This is another thing which was a new finding. Next thing was minimal effect of strain rates. We did not find a lot of effect of strain rates. So something which you increase in strain rate, it did not have a lot of effect. So and prosthetic mesh indicating, so strain rates are not dominating because prosthetic mesh was the more of the dominating factor. That being the load bearing component, because prosthetic mesh is not like a soft tissue. It's more of a linear mechanical property, of course. So you have a material which has almost a linear mechanical property, and you have a material which has a non-linear mechanical property, right? So we are looking at materials which are pulled together. So there is minimal effect of strain rate, which means that most likely some effect is dominating. We know there is a maximal effect of strain rate whenever you have soft tissue. So that stated that most likely there is a domination of the prosthetic mesh in the load bearing condition, due to which there is a minimal effect of the strain rate, because otherwise the strain rate effects are apparent. So if you look at the prosthetic mesh, minimal effect of the strain rate, these are the top 3 results. The pelvic tissue surrogate, maximal effect of the strain rate, quite a bit of effect. Overall properties, sutured prosthetic mesh, pelvic tissue, different strain rates, minimal effect. So we found a lot of interesting results which cannot be found using just medical knowledge. This can only be done using biomechanical testing and through having an artificial tissue, right? Further results, what we found using computational modeling, which were even more interesting. What we found was, which we could not see using mechanical testing, the maximum stress on the prosthetic mesh was at the location of the sutures. So the prosthetic mesh, where exactly the stresses were there, that was at the location of the sutures, which is fairly intuitive because that is the place of transition. At around 50% stretch, maximum stress on the prosthetic mesh approximately was twice the average stress observed in experiments. Right? So prosthetic mesh, all of a sudden there was a huge increase in the stresses, stress localization. So there are 2 types of stresses. One is the average stress, which you see in a UTM, and one is the peak stress. So the peak stress at a certain particular location was super high, and that is probably the reason the prosthetic meshes are failing. Because if you're testing meshes in a UTM and they're still failing, there must be some reason, right? The reason here is the stresses which you're seeing in a normal prosthetic mesh pulling is quite different versus while you're pulling it with the suture and the other soft material, which is your abdominal tissue, is almost twofold of that. So that creates a pinpointed stress which can be only found out using finite element model. Significant stress concentrations were seen in curved strands of the prosthetic mesh. So if you look at the strands of the meshes, what we see is, we see significant amount of stresses in certain places which are the curved strands, not in the other places, and a very high stress close to 90 megapascals on prosthetic mesh strands at a high strain rate. So high strain rate in our experiments did not tell us a lot of story, but here when we saw in the computation, we saw huge amount of strain localization or stress localization in certain regions. So what we could not visually see in an experiment, we could visually see some components of that over our finite element model. So this is what I wanted to capture. Finally, there is this rotation. What you see in the bottommost picture is a mesh curling, where this entire system is curling or rotating. This we also saw in the computational model, and we could effectively understand what is the amount of curving. So due to a particular suture, so tomorrow if I want to use any mesh, I can now have a testing model using my artificial abdominal tissue. I can do the mechanical testing. I can also do the computational modeling, where all I have to do is I do the mechanical testing, get the properties, fit it in my computational model, which is almost ready. The only difference would be the mesh properties or the mesh structure. which I have to maybe remodel in those cases. But once I change those, I can use the same method and look at what is the amount of twisting, giving metrics to what is the amount of peak stress. Based on that, hopefully I'll be able to advise to some of the medical device manufacturers, like who are into the mesh business, that this particular mesh, while we have tested it, was found to be kind of non-compliant with these kind of abdominal conditions, like which is typically hernia. So that is something which is more of a societal contribution. Have we reached that phase? Not yet. There are a lot of optimizations and studies which have to be done, lots of clinical tests which have to be followed with that for validation. But these are the first few steps in which our artificial test models for the human tissues have been serving to be extremely useful, right? And also what we found was the structural repeating unit of the prosthetic mesh influences stress distribution. This was another key finding, which told us that the design of the mesh knitting pattern actually influences the way the mesh is going to function inside the body. So such pieces of information were never known. Just because we started digging into this area, we were able to come up with all this information. So with that, that is the gamut of like the things which I wanted to showcase, like development of the artificial tissues, followed by like what are their key characterization techniques, and some of the applications out of many. Everybody is welcome to read some of our articles in what all areas we work on. We work on skin grafting, we work on prosthetics, orthotics, development of a lot of insoles. Many of our results are captured in these three books. The first book is known as Mechanical Properties of Human Tissues, where we have found out all the human tissue properties. We have basically reviewed all the properties from the head to toe. So anybody is using any human soft tissue properties which they need for their computational modeling or any kind of like experimental modeling, this is the book to refer. There we have all the models of the soft tissue properties, right? Next is soft tissue simulants. Using these properties, we have been able to create a range of soft tissue simulants which are for different purpose, like from eye simulants to skin simulants, heart simulants. We'll be coming up with some more versions of this book as more simulants are getting developed, right? So this captures some of our work so far. And there is another book with the along with the collaboration with Professor Sarabjit, which is on materials for biomedical simulation. This was more of an edited book, like where we had a lot of articles based on which materials for biomedical simulation, where we had also some contributions in the area of soft tissue simulants. With that, I would also like to invite everybody, like, as a part of my presentation, to lots and draw your attention towards a lot of the special issues and book series which we are running. So would like to invite everybody to contribute a book to our biomedical materials for multifunctional applications, which is an ongoing book series. And I'm the co-editor along with Professor Sarabjit for this book series particularly. So we are in charge of acquisition and everything. Next part is there is a special issue which has just started in the prosthesis journal, which has an impact factor of 4.5. This is on finite element analysis and prosthesis and orthosis research. So everybody is welcome to contribute their papers in this particular issue. I thought these all areas would be relevant. And the third one is I've recently become the associate editor for the Journal of Applied Biomaterials and Functional Materials, which would also appeal to the community. And we have started a special issue which is termed as Artificial Tissues Development, Characterization and Application. So I am the editor for this particular special issue. This is also open for submission. This has an impact factor of 3.1. So with that, I would like to acknowledge all my collaborators who have been extremely instrumental. All this work could not have been done by myself or just my students. I would like to thank my students and all the collaborators who have been very instrumental. We have recently got a huge DRDO grant, like, to build human tissue simulants for ballistic testing. We have worked with University of Alabama, Pittsburgh, AO Spine. We are also part of the UQ IITD Research Academy and few other entities, like, which are all very important collaborators for taking our research from lab to market. And with this, I would like to thank you all for listening. And I'm really hoping that some of these things could be useful or beneficial to all of you. And I look forward to having some questions from your side. Thank you.
Very nice, Professor Arnab.
Thank
Very
you, sir.
informative. And any questions from the participants, please? Any questions? Any doubts?
I'm also happy to share my slides, and if anybody has any questions later on also, you're happy to reach out to me. I'll
Yes,
be very much receptive to answering questions. So any questions, any queries, like anything from anybody? So really looking forward to this nice platform, and thank you so much, Professor Sarabjit, for inviting as always. And like I'm hoping that we could forge further collaborations within this community, given we have such exchange of knowledge and everybody got an idea of the kind of research we are doing.
yes.
Always a
Sure,
pleasure.
sir. Sir, from the behalf of our FDP, we also thank you, sir, for sharing
Thank
your
you.
experience on soft tissues and their analysis. So your invaluable insight and expertise with us is very sir. Your lecture provided us with a wealth of knowledge and latest development in soft tissue and development of various prototypes and testings. And we really appreciate your time, even on Saturday.
Right.
You have given us time to deliver your knowledge to our participants, sir. So, from the behalf of again, sir, from the behalf of our FDP team, we are very grateful to you that you have spared our time to and
No, thank you so much for having me. I think it's likewise, like, so very happy to speak in this forum, and I'm really looking for more such avenues to interact and collaborate. Thank you so much for having me, and everybody for listening.
yes, sir. Thank you, sir. Thank you, sir. Thank you very much.
Okay, thank you. Yeah, bye.
Bye. Let us wait for 5 minutes. Our next expert will join us and take a rest for 5 minutes. Then we will start a new session. This session of this FDP, followed by your test. Actually, the test is scheduled from 6:30 p.m. to 7:30 p.m.
Good evening, Dr. Sarvji, sir.
Anshaji, please, sir.
Sir, I think next resource person has joined us. Dr. Ravi Prakash sir has joined us.
Okay.
Dr. Ravi Prakash, can you hear me? Good evening, sir.
Hello.
Yes, sir. Good evening,
Yeah.
sir.
Yes, sir.
Good evening, sir. Good evening.
Sir,
So,
my name is. Yes, sir. Continue, sir. Sarvji, sir. Continue.
okay. Welcome, sir. Ravi Tripathi, sir. Welcome
Thank you.
to
Thank
our
you.
FTP. And we are very thankful that you agreed to deliver the lecture in this FTP, sir. And sir, if you have a permission, if you give me the permission, I want to give a short introduction about yourself to our participants, sir.
Yeah, sure. Thank you. Yeah.
So, Dr. Ravi Prakash Tripathi is an assistant professor in the Department of Physics at Punjab University, Chandigarh. He obtained his bachelor degree from Varman College, Bijnor, followed by MS from Indian Institute of Technology, Delhi, IIT Delhi. He earned his PhD from Indian Institute of Education and Research, ISER, Pune. where he worked on advanced optical phenomena in nanostructure system. Following his doctoral study uh, following his doctoral studies, Dr. Tripathi pursued the postdoctoral research at States, serving as a postdoctoral fellow at University of Alabama and later at Missouri University of Sciences and Technology, US, for a total of 3 years. His research interests span nanophonic, plasmonic, non-reactives, and ultra-fast spectroscopy, with a focus on light matter interaction at a nanoscale and their application in sensing, energy harnessing, and advanced materials. He has contributed to the development of novel optical technique and has a keen interest in bridging the fundamental physics with real world application. Thank you, sir. A very interesting short biography. So I request you to kindly you begin your lecture.
Yeah, thank you for your kind introduction. I am just curious whether my slides are visible or no. That's my first
Yes,
question.
yes, sir. It is visible, sir.
Okay, perfect. So I'm just and this laser is also visible, right?
Yes.
Yeah, perfect. Thank you. Thanks for the kind introduction. So myself, Ravi Tripathi. I am working as an assistant professor, Department of Physics, Punjab University, Chandigarh. So this is the title of my talk: Plasmon Enhanced Light Matter Interaction for Engineering Advanced Biomaterial. And some of the work I have done during my PhD, and right now I am just setting up the lab at Punjab University for doing single molecule source and other optical experiment, which may combine with these plasmonic material with the biomaterial and biological process phenomena to understand these aspects. So this is the outline of my talk. So I have just I am not familiar with the background of the audience, so I have just kept it from the basic, and then I will build on the basic, and then we will go to advanced experiment, which is currently happening throughout the world. And then in the last, I will discuss with the challenges and the future outlook, what we can do and what has been done and so forth. So the first question what we ask, what is light matter interaction? So this is the slide which tells about the understanding of light, what is like dual wave duality principle. So I hope a wave duality principle everyone will be sort of familiar with. So when we talk about light, so it work in two aspects. One is like wave nature and another one is like particle nature. So wave nature is like we can say like when when we perform the experiment from the young double slit experiment, if it is a particle nature, it should not be coming from the two slits. So it should not like we when we get the like pattern, so it should maximum at the one particular slit, and it should be decaying from the other slit. But when young double slit experiment was performed, so Young's found like it is not the case. So he concluded that the wave
Hello.
has the, like light has the wave nature, and the other aspect, when Einstein
कौन
performed
बोले?
sorry, hello,
हाँ जी, हाँ जी.
uh, is there any issue with
हाँ जी, हाँ जी,
like
बिल्कुल.
Dr. Ravi sir, your presentation is not in, I mean, PowerPoint mode. I think it is not.
no, it is in PowerPoint mode. One minute, I will just check. Is it visible
Kindly,
or
Last,
it is visible, but
last से भी शुरू
it is
से
not in slideshow mode. Sorry.
शुरू से ठीक है.
Yes, sir. It should be in slide mode, sir. It will be more convenient for
one
us.
minute?
Good.
I think right now yes
ठीक है,
or
ठीक
no.
है.
No, sir, not yet.
ठीक है.
Just check. Just check. Done? Is it fine or no?
No, sir.
because I am putting it.
Just try to
Sir, you
close your
click on
PPT and
slideshow
again
mode.
start. Could you please?
Yeah, I
Sir,
am
click
just
on
putting in the slide mode. I will just
Can
change.
anybody else tell
Sir,
whether
click
it
on
is in?
slideshow. Click on slideshow, then click on the PPT mode. Click on the slideshow
1 minute.
on the top corner.
Slideshow, yes.
Yes,
Click
yes,
on
sir.
that.
Yeah, click here.
Where?
Sir, in the
Now I have
top
put
column.
on the slideshow mode.
Sir, click on slideshow.
Yes, I have clicked on slideshow. So right now it is occupied. The whole screen is occupied with the slide.
Okay, it is not showing here.
Sir, it is, I think your side, it is visible to you in slideshow mode, but we are not able to see in slide show mode. I think there is a
1
problem
minute. I will
regarding some.
just again check it
Yes,
and then.
yes, sir. Kindly share again, please.
Yeah, 1 minute. Just give me a moment. Now, can you please check?
It is
Can you please
it is visible, but it is blur, sir.
blur?
Yes, I think there is some connection issue.
Okay, because I have put the slideshow and it is right now in the PPT one. So I don't know how to control that one. That is the thing.
So try to click on F5. It will
Yes,
work.
F5. Yes, I am putting in the slideshow mode. Yes, and then
Start from the beginning.
start from the beginning. Yes, yes. From my end, it's done.
Okay, so it's maybe some problems.
Sir, could it possible for you to rejoin the meeting?
Yeah, 1 minute. I will just rejoin it. Okay.
Participants, please wait for some time. A resource person is trying to rejoin us.
So may I have permission to give some announcements to the participant? And dear participants, this is our last session, and you can have your test for this FTP will be activated at 6:15 p.m. and you can find this test in your login ID. Then you in a login ID go for the assessment. There you find the questions, and from your login ID you have to give the answers. So 32 questions should be correct for the issuance of a certificate. So again I will repeat, sir. At 6:15 p.m. the questionnaire test will be activated, and a minimum 70% marks, or I can say 32 marks, you have to score to a certificate. Thank you.
Dr. Ravi, sir, could it possible for you to share your screen, please? Your mic is mute, sir. Your mic is in mute mode. Kindly unmute yourself.
So now, are you people able to see that one, or still it has some
Yes,
issue?
put it in your slideshow mode, sir.
Yeah, I have put it.
There is something issue, sir. We are not able. Anyways, let us pursue with this.
Anyway, I
Can we,
will,
sir?
if needed, I will send this PPT to the audience after the talk. So if
Participants, if you feel if you face any difficulty or you want to ask any query in between, you can unmute yourself and ask the query, please.
yeah,
Thank
yeah,
you.
that is perfect. Yeah, perfect.
Yes, you may
Yeah,
proceed, sir. Thank you.
yeah. So, when we talk about the wave duality principle, the light shows dual nature as like particle and the like wave. The two famous two famous experiment, we understand that, like one is double slit experiment, which is Young double slit experiment, which demonstrated like light behaves as a wave. And on the other side, when Einstein gave the theory of photoelectric effect, he argued like it is a particle nature. It has the particle nature. So the similar like Compton effect. So the next question we what we ask, like why this dual nature is pretty much relevant to us, like in the context of biomaterial. So in that context, uh, it has twofold aspect. One is like wave, which provides the fundamental to get the spectroscopy and imaging purpose, and the other one is it provides the particle nature, allows us to precisely quantify the energy transfer, like absorption, fluorescence, and Raman scattering. And so these are two processes. So next question, what we ask is like when the light is impinged on the matter, like in general any matter, what happens, how it does interact, and what happens to the like nature of the light. So when light interacts with the matter, the four fundamental phenomena take place. Like one is absorption, second one is scattering, third one is reflection, refraction, and emission. So this is the schematic which oh, sorry.
Excuse me, sir.
Yeah, sorry.
It's not moving.
Now it moved or no?
No, sir. Any other participant can please verify it. Any other participant, please.
No, sir, it is not
Is it
moving.
moving or not?
Not, sir.
Not moving, sir.
Yes, Dr. Ravi, sir, you just try to move from this left hand side from your PPT side, na?
Uh,
As you had did earlier. Recently, you have did na move. You have moved slides from left side of your screen.
1 minute. This way.
Sir, view screen mode, full screen mode, if he is able to present, then it will be good, sir. If he presents a slide in full screen mode.
Yeah, I am from my end, I am having the full screen mode.
Yes, sir. Yes, sir. From there only. You can move slides from there only.
Okay.
Where it is showing slide number 1, 2, 3, 4.
Okay.
Yes, from there only you can move.
Okay, fine. So now things are working little bit fine, or still have the issue?
Yes, sir. Yes, sir. Now it is better, sir.
Okay. So yeah, so the next yeah, so I think I have left one. So yeah, so the next point is like which is highly relevant for such kind of analysis. The other one is EM spectrum. So electromagnetic spectrum. So this is the schematic which is showing the this one. So this is electromagnetic spectrum of the biomaterial. So you can see like we always feel heat, like visible light can penetrate our live tissues up to certain extent, and UV can penetrate very little bit in the skin. So like UV can create the like cancer cell and other aspects. So EM spectra of the biomaterial becomes important, and few examples we have in our daily life, like X-ray. We use these X-ray beam for the imaging purpose, and other one is like heating the rotation of the biomolecules for biomaterials. We use the microwave, these microwave system. And the other one, what we like, sometimes we in the childhood we perform the experiment like with the torch, like we put torch light on our hand, and then we see like red color light, so that is like our hemoglobin spectra. And so these are like a complete spectrum of the biomaterial. And the another experiment which we encounter with the daily in the daily life, like green colors like of the leaves, and these different kind of vegetables, different colors of that vegetables. So these are like spectrum. These are the importance of the spectrum of biomaterial. The next we come up with the like how the light interacts with the matter. So as we see, like when the light impinge with the matter, it can perform like a different kind of experiment. One is like absorption. Another one is like light can scatter in different way. Like the scattering can be in two different ways. Like one is elastic scatter light, and another one is inelastic scattering. So elastic scattering is like Rayleigh scattering, where there is no loss of energy. However, when we go for inelastic scattering, there is a kind of either gain of energy or loss of energy. So it provides the like kind of molecular fingerprint to us to detect that which kind of molecule and what is the nature of the molecule. The other one is the reflection and refraction. So reflection, this schematic shows like when the light is getting, we are getting some light on the, like this schematic, the apple. Most of the light is getting absorbed. Only the light which is like red has been reflected to our eyes, and we see like the red color apple. And the refraction, the this experiment when we have performed in our childhood, like when we put the pencil or some vertical structure in the inside the glass, we see like some kind of broken structure that is based on the refraction of the light, and this is the governing principle. And the other schematic, which is this atomic diagram, which is showing like we impinge some light, the molecule gets absorb the energy, and it goes to the higher energy state. And when it comes from the high energy state to low energy state, depending on the from which level it is making the transition, we get corresponding light, and that we call it fluorescence light or emission. So emission can be in two ways. Like one is spontaneous emission, which we see like when we go on the road and we shine the light on the like strips, so it normally emit the light, and we get like shiny white light. That is like spontaneous emission. And if this emission is induced or like performed in presence of external field, then we get like stimulated emission, which is the basic principle of lasing action, what we see in lasers. In addition to this emission, when we talk about the emission process in more detail, so we see like when we impinge some light on the matter, it absorbs the energy, and the energy which it absorbs, it doesn't keep that energy for a longer time. It dissipates that, and the matter dissipate the energy in different pathways. So it may be the different radiation pathways may be in two ways. One is like radiative, and other one is like non-radiative. So non-radiative generally ends up with the like heating the element, or like some kind of internal conversion of the electron or like atoms from one level to another level. Most of for our interest, this radiative transition pathways are for our interest, like vibrational relaxation or energy transfer quenching, fluorescence and delayed fluorescence or phosphorescence. So in these aspects provide us the basic fingerprint of the molecule and different kind of phenomena, which tells us about the basic nature of how the biological process is going on, and how we can understand the process using this understanding of probing these energy relaxation pathways. So the next, these are the few examples which we see or we encounter in our daily life, like hemoglobin absorption spectra, which is red, and photosynthesis pigment absorption, like in case of like these these like leaves and all. So, and then another one is like protein DNA UV absorption, which we use to detect like and to study the DNA molecules. And the in last one, the IR vibration spectrum, we always familiar with the like surface enhanced Raman scattering. We use that one in our vibration modes study of the biological molecule. So next question comes like when we talk about like light matter interactions. Another question is like how we can tailor this property for our probing the biomaterial purposes. So basically tailoring the property of optical properties of these materials. So then the material has like if we see the broad spectrum of the optical property, so material property has like refractive index, extinction coefficient, dielectric function, and which basically bifurcate between the metal and dielectrics. So which metal we can use for probing the biomaterials, and which may not be selected for like probing the these biological process and all. Like silver is supposedly toxic in case of when we try to probe the biological molecules, whereas the gold is considered as a noble material for probing this or like investigating the biomaterial. So based on like recently the people are working in the like dielectric materials, they are opting instead of this one gold and silver, they are opting for the dielectric material, but the research is still in like embryonic stage, so it is difficult to say. Next we come like what is the fundamental of plasmonics. So when we talk about the light matter interaction as interaction in biomolecules or like biomaterials, so basically we are dealing with the nanoscale system. So when on top of that, when we uh,
Participants, please keep your mic mute.
yeah.
Yes, sir.
Yeah. So next, essentially we are dealing with the light matter interaction at sub wavelength scale or nanoscale. So and another point when we talk about the biomaterials, so the signal efficiency is pretty low because biomolecules absorb the quanta of light in a very less quantity, and on top of that, it produces the signal in a very low. And when we talk about like higher order nonlinear signal, it is pretty small and very, and they mostly tend to decay. So in that aspect, so we, sorry, any
You may
question?
proceed, sir. I have mute the participant from my side. You may
Okay.
proceed, sir.
Okay. So then then the question we ask like how we can enhance this signal. So then the role of plasmonics comes into the picture. Like plasmonic is like nanoparticle or like like nanoparticle and collective oscillation of the collective oscillation of electrons in presence of optical field. So first I'm just going through with the why nanoscale matters. Like as I have discussed, like surface to volume ratio impact the absorption and scattering. Basically we want to enhance the signal intensity. And another interesting aspect, especially for the metal and dielectric case, when we impinge light, and so the light get confined in between the system. Like you can see this computational simulation on in one nanoparticle. When we put the polarization along the one direction, it gives the intensity which has the electric field intensity ranges from 0 to 15. In the similar way, the in other one we have like nanoparticle dimer, gold nanoparticle dimer, which has like electric field intensity which is ranging from again 0 to 15. However, when we switch the polarization in the other direction, it gives the electric field intensity in between the, between these two nanoparticle space. It gives the multifold electric field intensity like 0 to 750. So basically, this particular point is called hotspot or like plasmonic hotspot. and this particular point is used to probe the biomolecules. The issue is like how to put the molecules in that nano cavity or like pico cavity. That is one direction of the research right now. I am also working, like we call it like cavity enhanced plasmonics. So we want to put the nanoparticle, put the biomolecule in between this cavity, and we want to probe the response of these biomaterials. So now come to what is plasmon. So plasmon is like effectively collective oscillation of free electrons in a metal, and the plasmon, based on this oscillation, whether it is a localized or propagating one, we can have two different type of like plasmons. One is localized surface plasmons, and then the other one is surface plasmon polaritons. So, and the other important aspect, like this plasmon is confined to the metal dielectric interface. When we excite it, it reside at the like metal dielectric interface. And the another thing is like when we can excite the resonance property, we can excite the resonance property only when light frequency of the light matches or perfectly matches with the oscillation of these electrons. So we call that condition as a resonance condition. So this is a schematic representation of whatever we have discussed so far. So this is the electric field which we have impinged on the nanoparticle, and based on the this positive and negativity of this electric field, the electron cloud gets shifted, and it start performing the oscillation. That's called like oscillation. And based on this frequency of oscillation, if it matches with the incident electric field, so we get the like resonance condition. The another important aspect is like if you generally just throw the light on some some metallic structure, you won't be able to see this surface plasmon, or like you cannot generate the surface plasmon. Why? Because there is a specific condition to generate the surface plasmon. That's called momentum matching condition. These are like the different scheme which we have have been explored, like Christman-Ortmann configuration, and another one like coupling with the prism. These configurations provide the extra momentum to generate the surface plasmon. So in this case we have like nanotip, and we put the we go the nanotip very close to the surface, and we generate the surface plasmon, and it propagate throughout the surface. In other one, we have like some kind of discontinuity on the surface, and which provide the extra momentum, and we generate the SPP. And in last, that is like we have some kind of nanoparticle structure on the film, and we impinge the light on this one, and we generate the surface plasmon polaritons. So as we have discussed, like two type of surface plasmons. So one is localized surface plasmons, which is like generated in small nanoparticle which have the like kind of curvature, and another one is like surface plasmon polaritons. So this one we have already discussed. This one we have produced the electric field, and we got the localized hotspot. And another one is like surface plasmon polaritons. We excite the one end of the nanowire, and from this end we get like surface plasmon polaritons, and it propagate up to the like micrometer length. And at one end it gives emission. When the discontinuity is there, the surface plasmon photon's recombine itself and then emit the light from this. And this end, which is like a plasmonic hotspot of the 2 nanowire junction, and another one you get the light from this end. So that is like propagation of light from one end to other end. And in this case we impinge the light from to both hand, and then we get the signal from this junction. So basically this particular technique has been used for generating like a single molecule surface enhanced Raman scattering. Then the same discussion like resonance condition for nanoparticle and field enhancement. So in case of polarization, we have like parallel polarization, and then the perpendicular polarization we have the electric field enhancement, which is like creating the hot spot. And this example, this simulation is related with the trimer, which has like three, this different distance is different, and this different distance is different. There we see like we have like very high electric field, which are like hotspot, very high intensity, and this one is little bit low, and the shape size of the nanoparticle is also different. This is very less like low size, and this is the different one. Now yeah, sorry. So now what kind of plasma material we can choose? So based on the our necessity, like requirement of the biomaterial, we can choose the plasmonic nanomaterial. So mostly so far the research has been done with the gold and silver. Now the people are now the researchers are working with aluminum, copper, based on the like whether we want to probe the biomaterial in near IR range or like ultraviolet range. So this is the spectrum which shows like for visible identification of visible probing of this biomaterial, the gold and silver are the two best option, and for near infrared, copper is the option, and for ultraviolet, this aluminum, magnesium, and other things are there. Now I come to the point like if everything is working so well, then what is the issue with the using with this plasmon for like chip or like lab scale or like chip scale when we want to industrialize this aspect? So the first thing we have like intrinsic dumping, like since we are dealing with the electron oscillation and electron phonon scattering, so they produce a lot of heat and most of the signal get dumped inside that one. Another one is like radiative loss. So the another thing is like getting the info generate, if molecule sends some signal, so how efficiently we can collect that signal. That is the another issue, which little bit I have worked on that based on the optical antenna during my PhD and postdoc. And another one is like another aspect is surface roughness. When we create a sample, it has like intrinsic roughness and some kind of fabrication defect, because we are going with the either top down method or bottom up approach. In both the cases it has the issue. And the and third one is the how to manage with like confinement and propagation length. If you confine the light pretty high, then the propagation length becomes less, so you cannot extract the information from that particular hotspot. Or if you have very less confinement, you cannot have like precise information from the biomolecule or like biomaterial to understand the system. So yeah, next, the how to combine the biomaterial with plasmonic systems. So one aspect is like you functionalize the surface, and then you integrate with the biomolecules with the this surface of plasmonic surface, and then you coat with this that biomolecules with those uh, to create an inert environment, so that the it is not interfering any kind of external issues. And next one is yeah, so next, what is the advantage of having this bio application? One is like you can operate in real time, and you can get the information at the real time scale. Another one is like it is compatible with aqueous environment, like gold and silver. Mostly we deal with these nanoparticle system in the aqueous medium. And third one is like we can miniaturize these concepts in for portable devices, and like and customize with the requirement. And the another thing is like when we go for like include these materials like meta material and other aspects, so we can use like one chip for having the different kind of sample to probe the biomaterial biomolecular signals and other aspect. But there are still some challenges are there. So what are the challenges? The other challenge is like fabrication and reproducibility of the signal, because each time when we talk about like nanoparticle having this enhancement, you cannot precisely control two nanoparticle, and you cannot put two nanoparticles at the same distance to get the same result at every time. Another one is like biocompatibility and toxicity. As we have discussed earlier, like gold has uh, no issue with the biomaterials. However, the signal efficiency is not good as like silver, but silver has the uh, biocompatibility issue. It is toxic in nature. So as an alternative, right now the researcher is using like core shell nanoparticle in one silver nanoparticle. On top of that, they are just putting some biomolecule and they are encapsulating with this structure with the gold structure, and that way they are probing this biomolecule system, and they are trying to understand that one. Another thing is like signal enhancement and detection limit. So signal enhancement is the issue which is currently there in for the system, because for biomolecule the signal efficiency is very less, and extracting that signal from that nanoscale or sub-wavelength scale is still a task. The people have come up with the idea of optical antenna. I will discuss with that aspect. So that they what they do is like involve one kind of plasmonic nanostructure, mostly silver nanowire or gold nanowire, and they send some information from one end of the nanowire, and that signal is getting at that particular location to the biomolecule, and then they extract that signal from that molecule, and then they from the other end, or like they put some biomolecule and other route from the other end, they just try to extract the information from the other one. And the third one is like miniaturization. This is the whole aspect right now, whatever we have discussed, like plasmon enhanced light matter interaction in biomaterial, that is still in the lab phase. And so far as far as I know, like there is no industrialization aspect in this one, and because of this concept, we right now the people are trying to get it in the like kind of chip scale, which can have like uh, multiple multiple probing of biomaterials, or like any kind of biomolecules in one slot. And another one is real-time monitoring. The another, like when you probe that one, you get some signal, you analyze that signal, and you come to the conclusion like this has some issue and that has some issue, but that is not in the real-time scale. So when the effective the effective aspect is of this the whole exercise is to get some kind of like to integrate this one with the biomedical application. So right now and then in that case, if you get some kind of signal from the uh, patient, and you extract that information, and you take some amount of time, so by the time you may lose the patient, or like the information is of no use. So right now the another aspect which the people are working like real time monitoring, how we can extract the information in the real time. So yeah, so now come to the final segment of the talk. So this is the few applications which some of them I have studied, and right now I am working on that, and some of the studies which has been done throughout the like world related with this. So first one is like single molecule search. So the why we are interested in this single molecule search, it has the like implication, biomedical application. Let's suppose some when we go to the doctor, sometimes we listen like you have come too late, right? So it means like we have the disease in our body, but it somehow, or like due to some kind of scaling issue, we couldn't have that identification whether we have the disease or not. But like we couldn't at that particular early stage, like early stage detection. So it means like the methodology what we are trying to explore right now, that is limited with up to certain concentration. So right now like researchers are trying to bring that limit to like very low, like up to single molecule, or like not up to single molecule, like few molecules. So one aspect is like surface enhanced Raman scattering, because surface enhanced Raman scattering is very particular tool to give the molecular fingerprint. If some molecule is there, the Raman spectra will be distinct from the other one. So if we somehow optimize the whole system with the plasmonic nanoparticle, we can identify the any kind of disease, with any kind of disease with this, using this technique like surface enhanced Raman scattering, and at very early stage, like few molecular system. If right now I think nanomolar or picomolar people are working with this one, but still again it is a like I think 2017 or 18 paper it has published. So it is like this is again, it is at very early stage, so it is the efficacy and efficiency is yet to measure. Another aspect is like can we detect can we trap some kind of nanoparticle with using optical field, and we can move that nanoparticle or like plasmonic structure inside the body. Why it is relevant? Because if we trap the nanoparticle, if we have like some kind of let's suppose the body has some defective cells at particular location. Right now what we the medicine what we consume, it somehow affect the whole body. But if we try to implement this particular concept, like if we trap the like nanoparticle and we drag it to some particular location, and then we detach it at that particular location where the cells are already damaged, and then we put the medicine at that particular location, like targeted medicine delivery, or you can say like target drug delivery. So that aspect it won't affect the whole body. So that is one aspect. So another thing is like if you trap the nanoparticle and you want to like drag that nanoparticle or nanoplasm nanostructure to some particular location to identify whether that cell is actually damaged or not damaged, so it will have some kind of signal. So that is like optical thermal trap is currently being used to understand the biomolecules and biomaterials. So in this experiment, the we have done like we use Dow prism and we excite the sample with this 532 laser system, and we trap the nanoparticle assembly at that particular location, and we identify the few molecular cells. I think this, in this case, we were able to go up to like nanomolar or like picomolar, and we were able to identify the single molecule detection or like few molecule detection at that particular range. And we have mixed two different molecules. One is rhodamine 6G and another one is like RGBs R 1 minute RG6. So two different molecules, and we were able to see like in one case we were able to identify this is the Nile blue event, and in another case it has like royal R6G. And then we were segregate these two events, like these are in different single molecule regime, and we were able to identify. And this particular image shows like we were able to trap this assembly of nanoparticle, and we were able to move from one place to another place, like this green, red, and black spot. And then we were able to move it within seconds, like 0 second and 12 second we went up to this point, and 40 seconds and 50, and then we were able to trap that, and then we were able to go from one place to another place. Another aspect right now the people are trying to understand in terms of like folding and defolding of this protein using this nanoparticle. If you have some kind of bead and you trap that one, and then you pull it back, or like you drag it towards one to each other, you can have like fundamental study how the protein folding and defolding is happening in the system. That's called optical tweezer technique. And another one is like this is the video, the recent paper which is published in ACS Photonics, where it shows like you can dynamically rotate and you can tune the nanoparticle basically based on the directionality of the laser. So I think this is visible, or it is only visible to me?
Yes, sir. Visible, sir. Visible.
Okay. So you can see like these nanoparticles are trapped. 3 nanoparticle system are trapped, and then we are trying to move it in one particular direction and other direction, so that basically it shows based on the directionality or like polarization directionality. In the schematic it is explained like it has one particular molecule inside that one, and then the 2 beads, and then we start rotating each other, and we are able to trap that one. So this was the recent study what we have done. And this is the another aspect, different aspects which right now the research is going on, like molecular manipulation, which I have just discussed before, and the cell manipulation. If you put instead of molecule, if you put some kind of biological cell or like tissues, you can also manipulate that one. And the same like this you can just drug delivery. This is the photoacoustic imaging. If you put some particle and you can enhance the signal, so basically like you can enhance the signal, you can do the ultrasonic detection, so that at early stage you can identify the disease. That is the this thing. And now I am coming to the another aspect which we have discussed, like signal efficiency or signal enhancement. So in this case, this is the concept which right now we are also working in this direction. So this is like you have some kind of transmitter, and you have engaged some kind of geometry which will be which take this information like free radiation you get from the free radiation, and you deliver that information to the uh, like to the object. So in this case you want to submit this information from this end to the other end, like the biomolecule is transmitting some information, you are extracting the information, and you get this information from this one. Or in the other way, like if you have some information, you want to send that particular information to the biomolecule, you engage with this some kind of plasmonic structure. It may be metamaterial or like plasmonic nanostructure, 1 dimension or 2 dimension, and then you send the information. The important aspect is how efficiently you can put this information to the receiver, or the same way like how efficiently you can collect the information from the transmitter. So that particular aspect is defined as a directionality. So this particular aspect right now we are working, like we are just building a setup so that we can have the information in momentum space. So because of momentum space quantify the angle, how much when you propagate some light from one end to other end, how the solid angle like theta and phi, how efficiently you can control that one. If you control that, the theta and phi angle, so it defines like how efficiently you can channelize the information to one particular end. So that is like called directional emission in optical antenna. So this was the concept of this. And the recent work which has been done in Cavendish laboratory, that was like interesting work. And right now we are working also in this direction, like single molecule search. So in this case what they have done, they have like one 2D surface, another one is like a nanoparticle in between, and they have trapped this molecule by surface functionalization. And this was like this cavity, the distance between these two cavity was like in the pico range, and they were able to detect with up to certain like single molecule, almost single molecule. And they argued with the like this is just because of like some kind of quantum effect as well, because when we go very close to beyond the like this nanometer scale, it will it narrow down to the like quantum effect. It start like asking the quantum effect in the system. So right now the like this is the published paper, but right now the people are arguing like whether we can have some kind of quantum information processing with this such kind of system using this biomolecules. So these are like current research directions. And this is also end of my talk. If you have some question, I'm more than happy to answer. Yeah, any question?
Dear party, if you have any kind of questions, kindly unmute yourself and ask your question. Dear participants.
Good evening, Dr. Ravi. Good evening, Dr. Ravi.
Yeah, good evening.
Yeah, I just wanted to ask you, since you have mentioned about most of metals here, gold, silver, and how about titanium is one metal we use very often. So can that be applied on this in the given concept? I mean, say, is there any work you feel in that area?
Yeah, so I have shown you this graph. So titanium is mostly it is not related with probing the probing the signal one, right?
Okay.
Currently we just this one we have discussed with probing the biomolecule process with optical one.
Okay.
I don't know
Okay.
titanium is having the response in the visible range or like near IR range, because most of the work what we do in the biological region, that is confined to the visible or an IR region. So I have to check whether titanium has the response, and especially in case of nanostructure, it has the response in those regions. If it is it has the response, then yeah, we are good enough to go because it is already
See,
of the
the
market.
only reason for me ask about that is because probably more than all of these metals, we particularly I'm a dentist. I think the audience has known me so further so far. So because in our area we quite often use titanium as a biomaterial for most of our. I mean, see, at most of the places we would want
Yeah.
titanium to be the prime material. That is why. Though we are using gold and silver also, but as you said, silver has its certain toxicity concerns, and that is why gold had been used earlier, but nowadays gold is not as preferred a molecule in
Yeah,
dentistry
you are
than
right. Yeah,
other
you.
materials. So that
Mhm.
is why I was curious to know how
Yeah,
titanium would behave in
yeah.
this
So
situation.
your question is perfectly relevant. The thing is right now, I don't know whether the
Okay,
titanium has the optical response, because right now we are
okay.
not replacing anything. We are just trying to understand the behavior of the molecule, how.
What's already in
Uh,
use, how they are behaving actually.
Yeah, so basically, we are trying to probe the molecular system so that we can understand the system. Like we can probe the disease and everything at the very low concentration, and how the biomolecules behave, and their behavior in the presence of high electromagnetic field, so that we can have basically biomedical application in that aspect. But titanium, it may be good option, but right now I don't know the range
Got
of
your
the.
point.
Yeah.
Maybe we get to know it over time. Maybe like
Yeah.
that.
Mhm.
Thank you, Dr. Ravi.
Thank you.
So any other question from the participant?
Good evening,
Dear
sir.
participants, please ask some questions as we are going to proceed for next test mode. Kindly
Good evening, sir.
ask if
Yes.
Sir, will this is, can be useful in the case of implants, bio implants?
Please
Actually,
repeat your question.
sorry. If you are asking about implantation, I think silver and gold will be costly, right? So I think implantation, of course, as one of ma'am has mentioned about this gold for dentist case and other aspect. But I think implantation will be having these gold and silver will be having a little bit cost, because when we do for the biomedical application, the testing and the cost effectiveness is also one of the concern. So the cost reduction should be there.
Sir, in the case of biodegradable implants such as zinc and magnesium, in that case,
No.
will it have any application?
No. So the thing is like implantation is bit different from what we have just discussed. We were discussing about how these diagnosis, because we are just curious to know how early we can detect the disease. That will.
My question was whether we can diagnose the healing of bone like that. Can we monitor that? If we in this biodegradable implant we are if we are inserting this thing, can we monitor how the bone is healing like that?
Yeah, that can be done. Yeah, that can be done by using this structures. We can do the imaging, and these imaging it can provide how the things are going in the positive direction, or it is not going in the positive direction. We can have that comment. Yeah.
Okay, sir. I'll contact you through mail if anything is
Yeah,
required.
sure.
I'm working on that.
Yeah, sure.
Okay, sir. Thank you, sir. Just nice session. Thank you.
I request Dr. Sarvji sir.
Yes,
You may proceed now, sir, for next.
Thank you, Professor Ravi Tripathi ji. A very interesting lecture, and I feel great that the last lecture is very interesting, and it's a new technology that you have shared so far, because in our previous days we are learning about the biomaterials and all these things, but in today's lecture there is a blend of physics in biomaterials, so it is a very interesting, sir. So thank you, sir, for sharing your invaluable insight and expertise with us today. Sir, your lecture provides us a wealth of knowledge and latest development in the biomaterial and surface engineering. We appreciate your time that you have invested in preparing and delivering the informative presentation, sir. So
thank you all of you for listening the talk. Thank you for invitation. Thank you.
Sir, if any participants wants to collaborate or want to interact with Dr. Ravi Tripathi ji, I will share the email of sir. You can so you can contact him for further clarification or any other type of collaboration you want to proceed. So once again, from the behalf of my FDP team, I am very much thankful to you, sir.
Thank you.
Thank you, sir. And now, dear participants, now we are going to proceed for a FTP test. So in this test, you find 45 questions and you have to complete within 45 minutes. If your score is above 32, then you will get a certificate. Otherwise, it is not possible for us, because everything is in automation, because not change anything. So all participants should log in to their account. So after logging to their account, they will find a tab assessment. Click on that tab, then the test link will be open. At 6:15, the test link will be activated, and you have to perform. You first read out all the guidelines of the assessment, that what should be followed. Switch off your mobile, and the responses will not be saved until you select the response and click the answer. Then at least 70% marks are required for being eligible for the certificate. Please ensure that you have a good internal connectivity before starting the assessment. So you click on I read and understand and start your test at 6:15 p.m. today. So after that, we have a valedictory ceremony in which we have a chief guest from the industry. So Until then, I request all the participants to prepare for the test and go for it. So all the best from the FDP team, and do your best. Thank you.
Sir, Dr. Savji, sir, I have one query in my mind. If in between, can I clarify, sir?
Yes, please.
If in between we got disconnected with the, I think other participants also want to know, if in between test we disconnect with the our internet connections or something like that, can we proceed for again?
I think the time is limited.
Okay.
That initial conditions they have wrote on the tab that you should ensure the connectivity.
Okay.
So the time is limited. After that, you can attend the test. It is everything is automated. There is no control in our hand.
Exactly, sir. Exactly, sir. That's why. So, dear participants, all the best for the test. Thank you.
Good evening, Sidhu sir.
Hanji,
Sir, do we
Hanji,
leave the meeting for that time or start our test at 6:15?
no, meeting and start attending the test. Then we'll again join.
Pardon, sir? Do we keep logged in the meeting also meanwhile,
No
or
need.
we can leave the meeting now, na, and we'll start the test at the site at 6:15. Is
Yes,
that
yes, please.
right?
I'm going to
Thank you.
close the meeting as well.
Right, sir. Right, sir. Thank you. Thank you, sir.
Dear delegates, I am going to close the meeting now. So we will resume the meeting at around 7:15 for the valedictory ceremony. In between, you can please attempt the questionnaire provided to you. You can also log out of the meeting and save your data also. So I am going to end the meeting now, and we will again resume the session at around 7:15 p.m.
Dear participant, try to be at 7:15 as the attendance may be taken. Dear participants, thank you.
पक्का तेज कर दो थोड़ी रख ली ना